think we're live again. Let's see if I can show around. Uh, we're in San Francisco today, in a place called Founders Inc. It's pretty cool. But we've got this sick view. I don't know if anyone can see it, but we got this sick view of some boats outside. We've got what's it called? The big red Golden Gate Bridge. It's pretty close. It's good vibes. It's good vibes to code Wi-Fi drivers. So that's what we're gonna do. Let's get my screen share up. See if it works. I'm still jet lagged a little bit from that crazy 2-hour time zone change, and also did a race last week. So I know I mentioned I was interested in streaming after the Tahoe Broken Arrow Sky Race, but it was like more than 20-mile run. Was definitely too tired. Needed to take the recovery time. Get our gameplay. Double check that we have everything working. Yeah, stuff's showing up. Things are working. What a time to be alive. I'm just gonna do the whole blast. I'm pretty sure streamers are supposed to do this before, but I don't have experience with this. So, c'est la vie. Cool, we've posted on the internet, and we're gonna post to the homies in Founders Inc. as well. Next few hours. Cool. Sick. All right. I don't know if folks can hear me, but I assume so. And I've also, to make sure we're in good headspace to code, I've got broccoli, the snack of champions for writing drivers. All right, quick recap. It's been 2 weeks since I did this, so I need to just get my head back in the space. What we're doing is implementing the internet, which means we figured out the internet is a TCP IP protocol. So it's basically just like a bunch of rules for how to break down data into zeros and ones, and then transfer it either as sound or light or whatever you want. You can actually build the internet using pretty much any type of wave. We're gonna use Morse code, and yeah, so that was the first stream. The second stream was, okay, how do we actually implement TCP IP handshake, or the TCP handshake, to be clear. So we wrote this high-level interfaces for how to do the three-way handshake, which involves basically one machine sending a request to connect, the other machine sending a confirmation and its own request, and then the third machine sending a confirmation. So it's called, these requests are called synchronize and acknowledge requests. So the handshake protocol in short is SYN-ACK. But basically, yeah, we went through that, implemented it. Now we need to actually do a Wi-Fi driver. So we need to encode packets in some way. So we have all these high-level calls, right? And just to refresh, I can run this script. Yeah, so really high-level client code looks like this. We have a server, we have a client, and a client can just do a open connection, can pass a port, and then we can send data, and the server can listen, and then this opens a listening process, which will be in the background, and then we can receive data on that. And how I've implemented these right now is really simple. We're doing these low-level packet calls where we basically send a SYN packet. We're waiting until we get a SYN ACK, and then we send an ACK packet. So right here, this open function is the TCP handshake. It's the state machine. And then in the listen function, this is the other part of the TCP handshake, the server is in a listening state. It waits until it gets a SYN packet. Once it receives it, it sends a SYN ACK packet, and then it's going to wait for an ACK packet. So again, the simple short is you have two people. If you remove all the verbiage, it's basically like you have two people talking. One person's like, hey, can you hear me? And then the other person's like, yeah, I can hear you. Can you hear me? And this person's like, yeah. That's it. That's TCP. It's, can you hear me? Yep. Can you hear me? Yeah. So one person's confirming, the other person's saying, yeah, I can. I got your message. Can you hear me? Like I got to double check that I'm not talking to no one here, right? I can't just respond to you and then not get a response back. So it's two-way. And now what we need to do is, like, if you go down here, these are like lower level function calls for how to deal with packets. So for example, let's use send a SYN packet. Right now these are just print statements. We gotta implement these. So that's going to involve encoding stuff as bits. We already saw the format for what a packet looks like. Basically, we can store both in here. So everything's IP packets. An IP packet points to a source and destination IP, and then the data within an IP packet contains a TCP packet. So that way we can use IPv6 packets, and we could send any payload. Like we could send data that represents a UDP packet. We could use TCP. We also found in the last stream that there's like a bunch of these like protocols. So there's like CubeSat, for example, for like, I don't know, a bunch of university nerds building protocol for satellites. And they can send data over IPv6, but then they have their own handshaking protocol. Say maybe, for example, if you don't want a two-way confirmation, you want to be faster, you can do a one-way connection. So you don't need a double handshake. You can just say, like, yo, data's coming. Server gets prepared, start receiving. So that stuff's all cool. Yeah, and I think now, like, the part we were just getting to, and where I would love for this stream to get is we should have all these calls implemented. So we're gonna need two things. We're gonna need we need to read and write to like files, like packets, and I mean, yeah, that's like the main thing. Like at the end of the stream, I should be able to run this client and server, and they should actually read and write packets to a file system. And right now, since we're mocking it, instead of sending these packets over a Wi-Fi connection, it's not overload Wi-Fi. Instead of sending them as a wave through the air, we're just gonna write it to the computer and then read it from the other process. So we're doing basically file sockets, which is a type of networking, but it's not wireless networking yet. And then in the next stream, we'll build the hardware. And then the hardware will be really simple. It's just gonna take a packet. It's gonna take these things, or I guess, what's it gonna take? I have to double check. Like if we're sending IPv packets or TCP, I assume we're sending IPv. Yeah, and basically, this hardware is just gonna take a packet as binary, and it's gonna just send it as Morse code to a receiving device. Yeah, so that's what's up. We'll see how far we get, but I think we're making progress. All right, so I think there's not much to do except just jump in. I want to see which part we want to do first. So also let me check my key mappings. Nice. So I got Zen mode. The simplest way to do this is just pick say, okay, what's first? The client. So the client's going to send an open request. The open request sends a SYN packet. Let's implement this. How's this going to look? Well, SYN packet is very hard coded. I don't want to be writing binary at each. Like I don't want to be doing this type of shit. In order to send packets, that's a headache. So we've got this struct, IPv6 packet, and I think we want to create a helper function, like a way to quickly initialize this. Let me double check the design. Cool. All right, I'm just opening up the interwebs, which I should probably move it onto the screen that I'm sharing. One sec. Cool. All right. So, I believe I attached a photo here at some point. Basically, I'm trying to see how the TCP and IP protocol, or how the packet is designed. There was a really nice, I think it was Khan Academy. I'm closing this little door because now I hear other people coming in and they will be pissed off if I'm just talking through the whole room. I'm not a student or a teacher at Khan Academy. So I want to compose these two things. All right, we got a header, we got data. TCP has its own data. So roughly what this is going to look like is, yeah, we have this 2 bits function in TCP and IP. We're going to have a def 2 bits. Send SYN packet. We're going to initialize a TCP packet. Sequence ACK. Yeah. So basically, we're going to pass in like whatever the key payload is, and then we're going to encode it as binary in this 2 bits function. And then when we create an IPv6 packet, we're going to create somewhere to pass in the TCP. So let's just do this. Instead of data, we're going to say TCP packet. Easy money. We're hard coding it. So in the future, we'd want this to be a generic, like a UDP or something. I'm just making it really simple because this is meant to only support one protocol. So that's kind of a design decision. I'd rather be explicit and like rigid versus abstract and implicit when you're making an MVP of something, because it's like, it isn't generalized yet. Like I want my design to clearly communicate that this doesn't generalize yet. This is like, I'm thinking about how to implement one protocol, doing that well. If we want to generalize it, that's separate work. Um, yeah, I see somebody's in here commenting. Yeah, we're gonna do it. We are building, well, at least a subset of the internet. Well, technically, we are implementing the internet, the main protocol. We had this discussion in our first stream, which was like, what even is the internet? And you realize it's basically a protocol that the military made for how to send data and agree on a connection, so that data is communicated reliably, and we are implementing that. So yeah, it's good stuff. All right, so TCP packet, and then what we're gonna do is somehow there's gonna be like bits encoded in here. Actually, this works pretty well. So if we want to convert an IPv6 packet to bits, we're literally just going to be like calling self.tcp packet 2 bits, right? So we're going to turn the TCP packet to bits, and then we're going to do bits plus equals. We're going to somehow make the source IP plus destination IP plus blah, blah, blah. Technically, this should come first. So maybe to simplify this, we'll just put it as a comment first. Wrong language. We're going to have a bunch of zeros and ones, right? And these zeros and ones represent the header for an IPv6 packet. And then we're going to append the payload. So it's like header, data. The data is just the TCP packet. And then we recurse into it where we call 2 bits on the TCP packet. Make it type explicit. Hey-oh. Does that work? Can I do that? Oh, come on. Is it? We do a ugly but valid technique. Front load it. I know you can do this in C++. You have to like forward declare the class. There, Python's like, oh, I've seen it. It's up here. That's kind of stupid, right? Like, look at that. Interpreted languages, am I right? Silly. Source IP, non-default argument, blah, blah, blah. Let's just set some defaults. All is right. Cool. So in here, we're creating a TCP packet. The whole point is this first call sequence. We'll make it very explicit. I believe sequence is 0, ACK is 0. Yep, I have a comment here explaining it. But basically, the beginning of the handshake is we're sending an ACK packet, or a sequence, or a SYN packet, pardon. And we're saying sequence is 0, meaning we haven't sent any data. ACK is 0, meaning we haven't acknowledged any data. I believe that's, yeah. So then in the future, we're going to say, okay, well, like we have, when we're sending like a SYN ACK packet or an ACK, we are indicating that we've received something from the server. And then with data packet, these are going to increment. Let me do a quick refresher to make sure I'm like thinking about this correctly. Again, realizing when you take a 2-week break, you basically can't take a 2-week break on projects. So I think last week was the Tahoe race. I was just too tired, but in retrospect, I should have still done like an hour or 2 just to keep your brain warm. Where is this? So I think it's like something in here. We had a nice article that explained this. Did I save it? Was I smart? I think it was in a previous stream. So here. So basically, TCP. There it is. I think it was as simple as just like, yo, the ACK number is the number of bits that you've received. And, oh, hey, Saho, welcome, bienvenido. the sequence number is the number of bits you've sent. It's pretty simple. Yeah, they're showing it here. So, yeah, nice and easy. Yeah, this is pretty cool. It's just like capturing how much data you've sent and received. So easy money. We'll start with like the SYN packet is easy enough that we don't have to think about that. But just want to make it clear, that's why we have it. Packet TCP. Are we missing anything? I don't think we need to send anything else for a packet. It really is just a data payload. And then the header. Maybe we could look at what the size constraints are for a packet so we don't do it stupid. Yeah. Yeah. Yeah, we figured out the size. There is a fixed size for this, basically. I think it was like 64. Is it bytes or where did I have this? Gotta like double check. 65. Yeah. 64 kilobytes. Yeah, 60. So it ends up being about 65K bytes. That's a lot. I think like a typical image is like, say it's like a megabyte or like an old school image. It's like a couple hundred kilobytes. That's like you could send that in a couple transfers. So it's pretty decent, honestly. 2 bits. Now we need to think. Okay, so got the data, sequence ACK. All we got to do is encode it to binary and then add padding. So maybe we could say, how's this gonna look? I'm trying to write it out here. Port number, destination number, sequence number, acknowledgement number. These two things. Port, we're just gonna just keep it simple and just be like port 0. Or maybe we'll hard code a port, just keep it simple. And each of these are 4 bytes. So 2 bytes, 2 bytes, 4, 4, 1, 1.1. That's weird. But all this means is we've got a bunch of zeros. We've got sequence and acknowledgement numbers, a bunch of zeros. And then we've got a data payload. So for our header, bits 33 through 64 or through 128 are going to be, or through 96, pardon. So these second 2 chunks are going to be valid bits. Everything else is just zeroed out. So I think the missing knowledge now is like a refresher on bitwise logic in Python. Like how do you operate on bits in Python? It's going to be Python I remember looking at this in the last stream. So there's like a bunch of libraries, but I'm curious just more on the fundamentals. Yep. Because I'm more curious, like, what do we want to do, and then look at the libraries and see which library supports us the most. 8 bits max. Character stitchers. Cool. Cool. Hex string to integer. Yeah. Yeah, so set bit is going to be we're going to do that using a mask. And you do it with, yeah, that makes sense. You're using a logical OR, so it's a single pipe. So let's write it out. Okay, say then we have mask. Okay, so say we have a string that's like an existing string, which is like a bunch of zeros, ones, whatever. Let's make it 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yep. And then let's say we have a mask of I don't know. Let's say it's the number 8. So it's going to be here. The logical or bitwise, I guess it's the bitwise or. What it's going to do is say, okay, look at the bits in the original and the mask and say if they're both zeros, keep it a 0. And if one of them is a 1, set the result to a 1. So we're going to have, let's keep it lined up. That's better. So we're going to have 0, 1, 0, 1, 0, 0, 0, 1. Basically what's going to happen is you're going to have the existing string, but you're also going to set these zeros to ones. So if it was a 0 already, and I guess the whole premise here is we're starting with a region in which the existing is all zeros. So I think the premise here is, okay, we've got a fresh bit string, everything's zeros, and we want to set this, say, region. And I guess say, okay, so think of the operations. So let's say our payload is, well, so I want to make sure we understand fundamentally like what a mask does. So a mask is just saying set the bits in here with the values in here. It's basically an equals. You can basically do an update from zeros to ones using a logical or a bitwise OR operation. Because you say, okay, if it's 0, keep it 0. If there's a 1 here, set it to a 1. That's the same thing as just being like set certain bits to a 1. So say we have a payload. So we have 16-bit payloads, 2 bytes, and we want to do like let's see, what do we got? Say it's say it's like that. And then we're going to have this longer string. So now I want to think of the existing, it's all zeros. How do we update a certain chunk of it? Now we need to do a shift, right? So if we want to set these bits starting at a certain amount, starting at a specific position in the existing bit string, we need to do a shift of some sort, right? How does that look again in Python? So Yeah, we have this offset written out here. Yeah. I wonder if there's a way to just like work around doing bitwise operations because it's super easy to get like off by ones and just like confused here. And if we just like use an array and then convert an array to bits, might be a simpler abstraction. Um, there must be somebody who's been like, let's simplify this. Mm-hmm. Does this do what we want? So what do we need? We need, for my helper function, we need an initializer. Yeah, so I think we can set that with length. And then we need an PS. Nice. So let's see what this looks like. Cool. This is a good example. So we can initialize with a certain length. There's going to be 10 bits, 3, 4, 5, 6, 7, 8, 9, 10. And then we're saying we want to set 3 ones at position 3. So it's going to start from the left, 0, 1, 2, 3. That's simple. This is the abstraction we want. So instead of building this, let's just use bit array. Let's keep things simple. How do I install this? Probably just pip, Yep, nice and simple. Pip install bit string. Wait, yeah, let's use vend again. Pip install bit string. Nice. Okay. Yeah, we already went through this loop of like, yeah. Oh yeah, we already went through this where we were like, let's install the thing. And then we oscillated a bit between like, oh, should we use a library? Should we not use a library? Just typically how I do things. I typically avoid libraries. And I think I'd be better off using libraries more. So the trade-off is using a library when you don't understand how it works. That's just going to waste your time. Yeah. So bit array length equals 10. Well, let's just initialize. Yeah. So is length equal, that's number of bits. So it's going to be something times 10. I'm trying to think here. So I'm doing a couple, backtracking in my head that like if we're sending data as Morse code, like as beeps, and a payload, 65,000 bytes, and each byte is 8 bits. It's a lot of beeps. Like that would be 65,000 times 8 beeps to send a packet, which is virtually impossible to send effectively. Which I guess is why OG Morse code sends like encodings of letters and numbers, because you can actually use beeps and compress the data much more. So yeah. So that's an A, B. Okay, so with like, now you have 26 characters or more. You have like 30 something characters you're encoding. It's much easier to understand it. So then that would mean we can encode everything as hex. That's just an optimization though. What I rather do is like make the payload smaller for the data part. But I'm trying to think through this, because this will be this is a key design decision now that we're getting down to the Wi-Fi. The Wi-Fi driver is like, can we push it off into the next stream? Probably, because we could just make the requirement that we're going to encode packets using the TCP standard, right? Like, I'm not responsible for the Wi-Fi driver. Basically, I was realizing that to build the driver, or no, to build the Wi-Fi device, sending with zeros and ones would be intractably slow because of the payload size. So we're going to actually have to come up with a better encoding later on. So Morse code's an option. We can do something else. But for now, let's just keep it simple. And we will assume our payload is this size. Let's follow exactly what they say to do. 2 bits. So TCP packet bits equals. Yeah, like that. I know this is like trivial, but like bits per byte. I still like having very clear constants rather than magic numbers, like this random 8, because it's just so easy to confuse like where a number comes from. And if you get one wrong, it's actually, you just change it by mistake. It'll haunt you for many a time. So bits. Okay, and then what do we got? Set seek at bit 32, set ACK at bit 64. And is that what we want? So like, it's 0 indexed, so 0, 1, 2. So if we overwrite at 32, it'll actually write it at the 33rd bit. Which is exactly what we want, because we want the first 32 bits to be the original payload, the port. Where is it? Where's that? Yeah, there it is. So 32 bits are this, all zeros. Bit 33 to 64 is like a sequence number, and then the next is this, and then so it's 32. Let's just get our offsets right. This is 32, 64, 96, 128. So starting at 32, the starting at offset 32, so the 33rd bit those next 32 bits are going to be the amount we want, the offset. And then, so basically bit 33 will be a 0 or 1 for the sequence number. Bit 65 will be a 0 or 1 representing the acknowledgement number. So those are the offsets. Yeah, so 33, or no, 32. And then sequence is always so sequence is going to be a binary representation. It's going to be an integer encoded to binary. So it's going to be a bit array. Yeah. That's a 32-bit. Oh, nice. They made that very simple. So we're going to take this unsigned int. Is that actually the correct? Yeah, sequence can't be negative. So it's an unsigned integer, 32-bit. The unsigned integer just means that if you're doing a signed integer, it means one of the bits has to represent the sign. So basically, if you have an unsigned integer and you want to represent the number 0 to 7, you need 4 bits instead of 3, I believe, because you need 1 bit to say if it's -7, 1 bit if it's +7. And if you're doing an unsigned bit, you can use that signed bit to actually double your range. So so say you have 4 bits, right? Let's just write it out. Signed, unsigned. Okay, say you got 4 bits. When it's unsigned, this would represent 15. So it's 1, 2, 4, 8. Sum those up, you got 15. This, I can't remember if the 1 represents negative or positive, but basically this would mean +7 or -7. And then like the opposite would mean, I think this would mean 7 and this is -7, because I think the first most bit indicates if there's a minus sign at the front. So this bit can now only mean plus or minus, which means you only have 3 bits left to represent the number. So it would be like you can't have this extra bit, which means you've just cut in half the number of values you can express. In other words, another way to see it is like with unsigned, or with both signed and unsigned, you're representing 16 values because you have 2 to the 4 bits. So 2 to the 4 is 16. So you have 16 combinations of values that you can express, except in signed, half of those values are negative and half are positive. So you've just cut the magnitude in half, but you now have a minus positive range. So it's the trade-off you're getting, but you're still representing 16 values. So we're using unsigned just to take advantage of that extra bit, because we don't need to store a sign. It's 32-bit, and then what do we got? 64. Let's get some sequence offset. 64. Yeah, we got an ACK offset. Yeah. There's a gnarly bug here that we would probably hit if we didn't use this library. I can explain it briefly, but basically, okay, say we've split our payload into 4-bit chunks, right? And then say you're wanting to say, okay, well, so say this is port so guest sin. So say these are the, like I'm basically compressing the definition into smaller little chunks. Say we wanted to set sin equals 1. If you just offset by 30 bits, or 32 or 64, what you're going to get is 0, 0, 0, 0, 1. Yeah, you're going to get that. So if you just offset, you have a sin bit, it's 1. You're trying to set it, and you're like, well, it starts at bit 32, so let's just shift 32, or in this case, in this example, I'm using 8. Chill, it's all good, it's the same thing. We're going to set a 1 here. Whereas actually what we want is this would be flashing the number 8, right? Because 8 in binary is 1, 0, 0, 0, 0. What we actually want is this. See the difference? So if you're flashing a 1 bit, we're not actually moving it. If we were doing this bitwise, like just one at a time, we weren't using this overwrite. Which I have to check if the library, again, like if I have to see if the library is actually doing what we expect. If we just trust it, we might have a gnarly bug here. So where, basically we try to set a 1. We've set an offset as 32. So it's going to make the first bit at position 32 equal to a 1. But this actually doesn't encode the number 1 in the payload because, I mean, let's just look at the diagram. So sequence number starts at bit 32. It's its own 32-bit sequence. To encode the number 1 in binary, it's 31 zeros followed by a 1. It's not 1 followed by 32 or 31 zeros, right? So like, and again, to explain this in decimal, it'd be like saying encode. Okay, so you got like all these bits. There's like encode 10 or encode 26 at bit 4. It'd be like going to bit 4, 1, 2, 3, 4, and then being like, oh, 26, boom, boom, like that. But it's like, no. Now this part of the payload is 2600. Like if you're reading it in chunks of 4, to actually put 26 at bit 4, it'd be like that. Because now you're trying to say like, no. Like in payload, in the region of our payload starting at the 4th bit, we want to encode the value of 27 in that little chunk. And numbers are right to left. Like in terms of magnitude, at least in our, whatever this numerical system's called. Anyway, so we have to see like how override is working here. Basically, we're trying to set the number 1. It's a 0 or 1. It's a bit length of 32. So this is going to be encoded as a bunch of zeros and then a 1. We need to make sure it doesn't just flash the number 1 there. So we have to check that. Wait, even new 95. Yeah, it generates the comments. It knows exactly what I'm trying to do here. Yeah, that would just be a hella confusing bug. So anyway, yeah, and that just ties in with my kind of rant about libraries. Because if you use something, you don't know how it works, you're boned. The plus side is look at the amount of like crap we'd have to do in here to like handle edge cases is a pain. So I think this is all we want really. And now we're gonna say data. Yeah. Data is gonna be starting at what? 1, 2, 3, 4, 5, 6. So 6 strings in. Each is 32. So this is gonna be 32, 64. 96, 128. To see how bad at math I am. Proudly shitty at math. 192. Right? Yeah, 32, 64, 96, 128, some other thing, 192. Cool. So that means bit 192 is where the data payload starts. We'll just say data offset. And just to verify, I'm reading this as bits, not bytes, right? 32 bits. Yeah. I mean, I think we can just do this data offset data. We're going to encode it as binary. We're going to cap that length at 65535 minus header size, which is 192. So we're saying like the data needs to fit so that the data payload amount plus 192 is equal to 65535. Which also means we need more. We got magic numbers. We got magic numbers. They're everywhere. Let's put them all here for now. Packet size. Then we got header size. 192. Data size equals packet size minus header size. And now we can just do this. Easy money. Cool. So see, I'm just trying to get rid of as many magic numbers as possible. Because like imagine we had, even in these 4 lines of code, we've got 1, 2, 3, 4, 5. We got 6 magic numbers. So it's like, if you don't make these explicit, you're just gonna get railed. Nice. I think that's basically what we want. That's pretty good. We've encoded this 2 bits, and that's our packet. Yeah. Now we can like test it. My inclination is to be like, initialize here, TCP packet. Let's encode the data of, I don't know, something simple. The thing we got to be careful here is ASCII is going to be different. Hi. See, so hi turns into that, and the number 0 turns into that. That's confusing, right? So if we want to encode the number 1, it's going to come out not looking like a 1. So that's gnarly. Maybe this way, the decimal number is 1. Yeah, so now we've got weird encoding stuff here, where like to send the number 1s and 0s, you can't just write 0s and 1s as strings. They'll get turned into something different in binary. I think we're gonna have to check this, but I think since we're initializing sequence and act as ints, not as long as these aren't passed in as a string. We got to be careful here with Python because it's dynamically typed. So basically, if it interprets this as a string, it's going to come out a very different binary than if it's interpreted as an int. Can we like make that safe? Python force argument types. This is parameters. force function parameter to be an int. You can add annotations. They're not enforced. Ay caramba. So I don't like dynamically typed stuff. Right, so okay. If you're watching and you're wondering like why that matters, it's because Python basically just lets you send anything. And then that's great when you're not doing binary like bit hacking. Once you're down at the bit level, you want to be really explicit of what your bits are being encoded as. And if you don't have types, that's kind of a pain. So I'm going to add like uint, sorry. Do we have that? Oh, I see. Uint 32. So it's not enforced, but it's something. Is it letting me do that? I don't even think it natively has these types. Ooh. We could just YOLO it and see if it's what we want. But that's spooky to me. Because like, again, there's a huge difference of like, if a number is interpreted as a uint and you pass in an int, it's going to treat one of the bits, it's going to ignore the signed bit, and it's just going to double your number positive, right? So if you pass in the number 10 as a int, but then you interpret it as a uint, it's just going to come out as 20, basically. Like it's going to double the value of it. So that's dumb. Or would it? No, it'll potentially increase your number a bunch if the sign is negative. Essentially, that's what will happen. Because it's gonna look at the first bit and it's gonna say if it's a 1, just like count it. If it's 0, don't. I don't want that to happen. So like, we can just keep it. Basically, we gotta watch it really carefully here. But I want to be explicit that this is an unsigned int 32-bit. How do I? Gotta import numpy. Yeah, it's very heavy-duty middleware. Oh man. Come on. Okay, let's just see what happens without numpy first. And basically, if this is a problem, we're gonna have to be explicit. But anyway, we got some data. We got high, we got 0. Just make it both 1 so we can actually check it. Nice. We got 2 bits. Gonna debug there. Gonna do that. Yeah. Debug. Cool. So we got bits. Should show them somehow. There they be. In their glory. Didn't like that. Didn't like that. Unorderable type bit array. The hell? This is backwards? Yeah, seems backwards, silly. Yeah, what is this? What is this silliness? Silly Copilot generating the arguments backwards. Let's see if that actually fixed it. That did fix it. Now it's going to crash there. Yep. Silly Copilot. Cool. Let's try it again. We got bits. We do. And you see it actually did it. I don't know if that's right. Let's see. Check the next one. Looks weird. Looks funky to me. Because that's the 16th bit. And then it's 1, 8. Maybe the debugger is just showing it. In a weird way. Can I index into a specific one? What's the, there must be like an at. Is there a get? There should be a way to, or is it just, I bet it implements the whatever these are called. Can I just like do that? Let me see. False. Okay. Yeah, we're definitely getting weird offset behavior. It's like the 15th bit. It's super weird. This is kind of the bit position to begin overwriting from. Well, said here, and we said the length. Oh, is it writing backwards? Might be doing that. Like, looks like the ordering is kind of weird. Like it's writing, let's check it again here. Okay, so I'm trying to just explain how it would show up in these two positions. Like, these offsets are 32 apart, but these two numbers are clearly not 32 apart. What do we got in here? Let's try encoding it here. Sick, not sex. Just encode these quick. So binary of ACK. Yeah. I think it'll give us some clarity to see like how these bit strings are being encoded in the first place. Yeah. Well, yeah, there it is. That's what we expect. So these are right. Sequence offset. That's too long. Can I copy the whole value? What happens here? Now we're getting deep. Got a binary file. We got any ones in here? We got a one. Yeah, we got ones. Here they are. So this looks like 32 bits, separating them. And yeah, that looks like what we expect. But then here we got more. But I think that's also what we expect. Didn't I? We should have a bigger offset there. I'm just trying to remember what I wrote. Nice. That looks like 92 or something. Sequence offset. Yeah. I mean, that looks like what this looks kind of like what I want. Well, here's the bits. There's no denying this. And then we've seen that yeah, these are 32 apart. So it's this initial offset is wrong. It's certainly not 32, is it? 1, 2, 42. There's an extra 10 bits just here. And I'm not sure why. That's weird. This is what I get for doing bitwise bit array work on a Sunday morning. I deserve this. Well, like what could the reasons be for this? So this is correct. So the 64th, and that also means that the ACK offset, well, the difference between the two is correct, but the offset of both is then incorrect, I think. I think that's what that means. So position is wrong. Is position being encoded as a different value? The bit position to begin overriding from. So where is position being used? They're not going to show me how to implement this function. Looks like it's defined in here. Can you imagine having to write this from scratch? Good thing we used a library. Oh, it's making me yawn just looking at it. Well, I'd love to know why it's doing that. I wonder if it's reading the offset in a way that's like smaller than what it should be. I just can't think of why it would do that. Let's Google. People being like, yo, this shit's broken. Python bit string overwrite position is wrong. Come on now. I know that. I know. Yeah, these people are talking about exactly the thing I was bringing up earlier. The classic mistake. I mean, so like the most guerrilla approach for how to get around this is just revert the offset. So maybe one thing I want to check is this consistent? So let me try this. Basically, I want to make sure that this isn't a random no, I don't want to put it in there. Prefix. So I want to try this. Just going to run it again. Just make sure it's deterministic at least. If there's some random noise, then that's a whole different thing. I always check for that because it's just awful if you realize you've got like non-determinism in something at this level. Yeah. Copy that. Copy value. Look at that. Doesn't look the same. So that is clearly not the not the same as the first time I pasted it. Oh no. Oh Lord. Looks different. Oh God, is it just randomly padding? It's terrifying. Boy, well, let's just see how incorrect the offset is. So it's supposed to start at should be here. Well, here technically. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 11 bits off for some reason. That's gnarly. Yeah. I really thought this was going to be easy. It's okay though. It's okay. We'll try this. Oh, nice. data offset. This is a string. Bit array should have a string adapter. Right, come on. Come on now. Come on now. Come on, buddy. So I think there's two problems here. There's like we have a weird offset thing. But then there's, can we decode it back to what we want easily? That's the part I'm more concerned about. I don't want ASCII. Did I write that? Oh. So we're going to convert to hexadecimal and then hexadecimal to binary, right? Makes sense. And then unhexlify. Okay, easy. So assuming we have the payloads, we can just do that. Nasty. Such a creative library name. What do you call a library that converts ASCII to binary? Benasky. Of course. So we will. Oh, where were we? We're here. Nice. So we got our there. So we're calling this library. We're converting self.data into. So we have a string. We're converting the string into hexadecimal. Base 16. I think that's what that means. Let me double check. It's probably a base. Bytes per separation, yeah. So 16 byte separation, and then we're converting that to an integer. And then we're converting that to a binary string. Simplest way to do this is just to send in some really clear data. So we know what high means here. We'll convert this to binary online to do like a double check, which I think we already got. Yeah. High. Convert that. So this is high in binary form. And then in TCP packet, we're going to, let's see. Here. We're going to see what it looks like. So just debug it. Yeah. Oh. It's like freaking out that you can't send a string. I thought that's the whole point of this function, is to convert a string. Silly Python. Isn't that like the literal example here? The tautological example is using a string. Oh, I see. They changed it. It's Python 2. Nice. That's always fun with Python, how they're like, oh yeah, you know, like Python 2, it's just different now. Silly. Hello.encode from bytes into bin. What does big mean? Come on now. I still want to keep this method. I was going to comment it though. I still want to keep it. I'm not done with this hexlify library. Benasky. I don't know what this big means. Let's double bytes. Oh, it's endianness. Big endian, little endian. What does that mean again? I remember hearing this. It just means the order. Place at the byte with the lowest address. So we're using, we're doing big endian. Yeah. Yep. We're doing big endian. So the biggest, the byte, the lowest address has the most significant bit. Big endian. That's what we're doing. This is not closed. The hell? There. Let's try it. This has got to be the most brutal stream on Twitch right now for coding. There's just no graphics. Just like, no, we're doing bitwise debugging for hours. Anybody who tunes into this is probably just like, what the heck is going on? Like, what is this? We're not even coding. It's just like, we're looking at numbers now. Did this work? It sure looks like it. Yeah. Yeah, that looks, yep. How many bits are there? If we split it by 8. Yeah, looks right. So at least that part's working. Oh, yeah. B-data. I need to figure out how to pass in this bit array thing. Yeah. Okay, simple. It supports B string. What is a binary string? I don't understand. It's a binary string. Yeah. I use length or offset. Oh, it's because it's already a bit string. So it's supposed to be like that. It might be because the length and everything's already strictly encoded. It doesn't let you truncate it. Yeah, that's right. Makes sense. Because like, yeah, you've already turned it into a bit string. That's what this library is using under the hood by the looks of it. So now we check. We got our bin. Oh god, there's too much shit. And I already lost track of what this all means, so let's just delete it. Copy. There's our payload. Is there a way to check that this is at the right place? Yeah, So we can do 192. Oh, that's right. The fuck? You know, this actually looks right now. Man, maybe I'm just like dumb. I might just be dumb. I think that's a valid hypothesis. So, yeah, I think the literal thing that I already pointed out earlier in the stream is this thing I got confused on. Because look at this. Check out this pro gamer move. So you go to bit 32. And you're like, why is there not a 0 here, but there's a, or why is there not a 1 here, but there's a 1 here? And you're like, well, because it's a 32-bit string, and so it's going to be 32 bits to the right of the 32nd position. So you go to here, and then you go 32, boom, there it is. To make sure we get the number exactly right. String starts here, meaning this is position 32, so 31 bits from this is the 32nd bit, right? Like 1 bit to the right is the second bit. This is the third. So the 32nd bit is going to be 31 to the right. There it is. So it is positioned right. Now we're going to move 32 to the right. Now we're at the next one. And then we're going to move 64 to the right. 64 to the right. Actually, how does this one work? Maybe I'm not. Okay, so let me see. I'm trying to figure out how we get to here now. 192. All right, 192. Here. Because we got this beginning string there. 192. There it is. Okay. So 192 puts us there, which is correct. That's exactly what we want. And then, yeah. And then 1 less than the final bit. So we do 32 and then 31. We go there. And we move 32 to the right. We get there. So all of our bits are actually in the right position. I'm just incredibly dumb, I think. And I'm also tired. Streaming's hard. Because you wake up and you're like, man, you know what? I'm sleepy today. I just want to sleep. And you're like, nope, I'm going to debug binary for multiple hours first thing in the morning. That's what we're doing. And I think now that I've shut up, it feels better. But it's definitely not easy. It's much easier to stay in bed. I can tell you that. But if we stayed in bed, we wouldn't be having so much fun right now. Yeah, we did it. We did it. So let me, we can do some assertions here. I think this is worthwhile. Yeah. Can we do this? I gotta use the restroom quick. I'll be right back. Don't you worry. I'm back. And I've got more cold brew, and I've got more coconut water. I'm gonna have some more broccoli. Then we're ready to resume. I think we got our bits aligned, so it's a good day. We're ready to continue. Sorry, I was muting myself while I eat broccoli because I have some respect for the stream. I was worried we weren't going to get out of that. I thought we were going to be stuck debugging bits for 4 hours. I was just like, I don't know. Anyone who codes understands that. Of like, you get in a rabbit hole and you're just like, well, I might never get out of this. All right, so prefix. I think we've. I'll just like run it. I'll run the assertions to like make sure. Let's see if actually Python lets me do this. I know there's an assertion primitive. Come on, no. Yeah, it ran. And maybe we want to do a sanity check that the assertion fails if say that's a 0. There should be a panic. Yeah, nice. So we're kind of like unit testing inline. Remove that, clean it up. It's good stuff. And I guess this 2-bits function, we don't want this assertion here all the time. We would want this down in the call site, which is syn packet. I mean, this is a unit test. That's what we've done here. We probably ought to test these a little bit. But just because I'm being jank. Actually, no, I think it's worthwhile. Test 2 bits. I think it's worth abstracting this into like a little test area. Yep. Did it just like know that? That's messed up. Yeah, I mean, this is technically we could use like pi unit test, but you know, this is just me trying to make it work. Yeah, we got there. Check those assertions, skip here. Yep, skip. Yeah, oh yeah, because see, if you call us with a different payload, the sanity check doesn't work. You can't do that. So you gotta pass 1s here. Yeah. Easy. The reason I'm codifying it here is because if I come and refactor this, um, not long from now, see again, like it's good to have a test because we verified it was working here, but then realized we're not returning the bits, we're returning something else. So super easy to just like think you've done it right and then goof something up. In this area, this causes so many headaches. I don't know what this is. This is like auto-generated garbage. I don't need to check that. Maybe I could do that 192. Should be. Well, let's check what the first one bit, I believe, is bit 192. So if I go here. Oh, it's terrifying. Fuck. Come on now. Yep. Yeah, 192. So the position 192 should be a 1. That's all I was checking for. So these are the three. We can do that's all we want. It's just making sure our offsets are right. I assume if these ones are right, the rest are, because they're all just relative. Yeah, cool. We should probably commit this because we've made progress. We spent an hour and 45 minutes writing this function. I would so fail the Google interview because I did not do this in 3 minutes or have it memorized. Oh, what do we got here? We got. I just want to commit one file here. Just keep it everything in main. Commit. This hasn't been tested well, but you know, it's okay. It's our little secret. Like the commit logs, it's like June 12th, entering binary land, and it's like 2 weeks later. Not representative. It's been less than 2 hours, but it makes it look like I was just in hell. Okay, we did the thing. I think that's pretty darn cool. See, keeping it simple is like if we had ports and stuff, then we got to go further and just like ugh. Just keep it here. So in the send SYN packet, we've created the TCP packet. Then we're gonna do IP packet. Yeah, we pass our TCP destination IP. Let's keep it simple now. So there's no, we're just setting a couple header flags. There's no payload in the TCP packet. Now we're wrapping the TCP packet here in an IPv6 packet for ports or IPs. We're mocking ports, everything right now. We're just assuming it's some fixed number, like it's whoever's listening. But there is this interesting thing where like, so technically speaking, a server could listen to signals on any, like it could listen to any data, right? It could receive your data. So if you're sending data over Wi-Fi, you could packet sniff, right? Which is a thing. You could use something like Wireshark. You can actually like listen into data that's coming. So I think one thing that's interesting is when you're sending data to another computer, it's not like you're pointing a flashlight at it where like you aim and then it hits the computer like photons. It's more like you're blasting waves. A lot of devices can listen into that. And then what happens is one machine agrees that it has the address that you have, and then it has like say a private key or something that it can use to decrypt the data you've sent. But if you're just sending raw packets following a protocol that's not encrypted, that's not hidden in any way, you can just listen to those packets. Like you could just look at network traffic. So if you're in the same house as somebody, you could just see what their browsing history is by listening to their packets being sent over the network. And that's why you need like encryption and everything. So people, I think that's cool because it's like it's demystifying the hacking a little bit. Like I think people have this understanding, or like non-technical people think that like hacking is this like weird voodoo thing, and it's like no, like packet sniffing is like a really simple way where you could be at like a Starbucks. Starbucks is a bad example because I'm pretty sure they have a standard encryption, but like if you're on a public network, in some jank hotel that doesn't know how to be secure, and they're using like old modems or whatever, you could just sit there in the lobby and like look at people's internet traffic, assuming there's no like encryption. And even if there is encryption, you could still sniff the traffic and then you can decrypt it. So you could download people's traffic, which is kind of interesting. And I guess I don't know deeper on this, but like one thing I'd be curious about is like, how do you prevent packet sniffing? Yeah, that makes sense. You can't really prevent it because if you're using Wi-Fi, so basically, if you're using Wi-Fi and you're sending data through the sky, people can intercept that and see what they can see your browsing history. Like that's the TLDR. So I think people have this assumption that like internet traffic's secure. And it's like it's not. We could just like we could probably build a packet listener, and then just like see anyone's browsing history in the building. But then we have encryption to prevent that. So that's the TLDR. Basically, your Wi-Fi data is not secure unless it's encrypted. So not worried about that right now. What we're going to do though, just finish encoding this IPv6 packet into binary. We've already got this part as bits. We've done a bit string encoding here up above. So we're going to do a similar thingy where we're going to define an offset, data offset. We need to figure out where the data part of a packet begins. Where is this? This is our nice Khan Academy article here. So the IP header is 32 bits, and then data starts at bit position 32, so bit 33. So we're going to do that here. And then we're going to do data offset. We're encoding the TCP packet to bits, which we've done here. And then, and again, we're avoiding implementing all this. We're using the bit array library. And then we're going to overwrite bits 32 onward with the data packet, which is our TCP. And the TCP packet contains the sequence and ACK offset to do a three-way handshake. So we've almost got it. Now I think probably be a good time to do a test that we've set this right. Let's move our test code. We're gonna need to split this into separate files, but you'll be surprised how far you can go before you clean up code. Here, let's do, we have TCP. Now we want to do def test IP 2 bits. So we got our IP packet. They've encoded it nicely here for us. It's a good Copilot generation. IPv6 packet. Yeah, packet. Let's keep our IPs as 0 right now. We could set it to 1 technically, but I am trying to just keep this simple. Let's just keep it at 0. I don't want to offset it. So if the data is set at the right place, then we can have our header defined anywhere. Sick. So 32. Basically, our data should begin at the beginning of the data payload. We'll check if that's the case. And then we'll call here test IP. Let's do a quick test. If that works, then we're ready to move on, essentially. There. Yep. 2 bits. Sequence. Yeah, that'll do it. What we're wanting here is actually this part. Oh yeah, we got to do this part. Okay, so we already agreed that a TCP packet is 65. Like we already defined the length, and now we're just adding an extra header for the IP packet. But I think the problem here is that a TCP packet includes that what is it? So when we're defining the size, this here is 65,000 bytes, and that's this part here, and then there's going to be an extra 32 bits on top for the IP header. So welcome, new people, hanging out in the stream. We're spending Sunday morning reading binary, if you like doing that for fun. And then next week we're doing hardware, which will be even cooler. So, okay, got our overwrite. Let's close this. Basically, we need to move this this packet size thing up a bit. We can just have an offset here. So we have IPv6 packet. We need to share this essentially. This TCP packet size. We need to make this a global right now because it's being shared in 2 classes, like that. Yeah. We're gonna rename it TCP packet size. I think it's only being used there right now. Yeah, sick. And then in the IPv6 packet definition, we're going to use it here. TCP packet size. Sick, bro. Got an error though, what's up? Expression cannot be assigned. I can do whatever I want. Opportunities are endless, dude. That. Yeah, it fixes it. we got these bits. We got our TCP packet. We're saying, hey, this is how big it is, because we already know that. And we're saying, hey, we're gonna put it at the 32nd bit, because the first 32 bits are the IP address. Shouldn't there be 2 IP addresses though? The IP header is supposed to be at least 64 bits. I mean, I think this diagram's wrong. Oh, but I guess no. I don't know. It looks like it's right. Source. Oh, that's the TCP header though. IPv6 packet header. Let's see the original definition. Basically, this source address, there's like 288 bits, something, where it's just a bunch of shit. So that makes sense. So this diagram logically doesn't make sense that Khan Academy is using, because it's clearly like, oh, they're right that it's split into 2 chunks, but they're not right that it's just like, they make it look like it's 32 bits. It's not. There's more stuff going on here. So when in doubt, let's go back to our friends at DARPA and see how they've defined everything. IPv6 spec. Let's go look at the original specification. 1998, Nokia and Cisco. We're gonna look at the header format. Can't make this up, folks. This is the real thing. Oh, where'd it go? I lost it. It's here. Boom. Doesn't lie. So that's a nice doc, am I right? Yeah, look at this. Look how slick this is. It's all ASCII. They've diagrammed everything, every single state transition. It's got an appendix. It's got citations. This is a research paper, which it really is. But basically, this is what we need. And now what they're defining here is, okay, here's the destination address. Let's see, what's the source address? 128-bit. That's important because, again, let's call out Khan Academy here. They said it's 32 bits across. This is wrong, incorrect. That would lead us astray. So I don't actually know why their image has that, but it's probably some editor that's innocently like, hey, let's just put a nice picture of a packet. Or maybe give them the benefit of the doubt, they're talking about IPv4 and not IPv6, but hey. Now that once we're reading the spec, we're becoming those people that are like, actually, it's 128 bits, not 32. But it's the way we live now. So what do we got here? 128. We can say there's a 32 across. So 1, 2, 3, 4, 128, 128. And then we got another 64 bits. What happens when you add those numbers together? Again, like I'm unapologetically bad at math. So got 128, 128, 64, 320. Okay, so the header for an IPv6 packet is 320 bits. Which means that the data offset is not 32, it's 320. So it's actually 10x. I think we should actually be defining that as a constant. IPv6, yeah. Header size, 320. Welcome to the chat, Lily. Te amo. I love doing streams because I love just seeing I love just seeing who shows up. Like it'll be significant others, just friends, just random. I haven't gotten trolls yet. I'm thankful for that. I'm waiting for the day where I start just having people come in and drop like Hitler memes, then I have to ban people. But I don't think we're at that scale yet. Cool. Anyway, data offset, originally we're just going to define this IPv6 header size to make it clear that the offset is relative to that. We can delete this. Technically, what we need to do here, this bit string has to be initialized by a certain length. Where did we do an initial setup for IPv6? Or not, for TCP, here, bit array. So we're gonna do the same thing. We're gonna define bits. It's gonna equal TCP, the length of our bit array is TCP packet size plus IPv6 header size, right? So it's a header plus the TCP packet. So now we know we have exactly the number of bits we want. And now we're offsetting the, then we're getting the binary version of the TCP packet, which is defined here. And then we're writing it in, and then we're gonna return it bits. So this is what we want. Yeah, test IP, and then 320. I don't know if it's supposed to be bit 320, but it's like, again, we're encoding the data hello. So if we check this as binary, where is it? So hello in binary is this. It seems kind of odd. Oh, I guess these are both L's, so we duplicate HELLO. For context, that's what all these are split up. So the second bit is a 1 in hello, which means bit 321 is going to be a 1 in our encoding. All right, we got errors. Got an unexpected keyword argument length. Yeah, that makes sense. We don't need a length here now. We've already created the bit string up above. That's just a typo. Let's try it again. Now we're just going to do a couple of runs where things are inevitably broken and we address what they are. That, yep, what's wrong now? Override exceeds boundary of bit string. That's a good one. It means we have an offset error. Oh, my favorite. Offset errors are fun when you're just dealing with zeros and ones. What can I say? All right. It's probably just like a plus or minus 1 we've got here that we shouldn't. So header size 320, right? The length of bits here we can check should be 320 plus 50 something thousand, whatever. Yeah. TCP packet size. There it is. You can see the bug. Just give people a sec if they can see it. The problem is we initialized a bit array of 65,535 here. Well, 65,000, whatever, plus this header. And then we said bits equals, and then we just overwrote the array we made up here. And because we overwrote that, we just shortened the bit string, and then we tried to override a position too far into it. So we just truncated our bit string by 320 bits unintentionally. So we actually need to do IP bits. Yeah, and then what we're doing is we're saying, okay, now we have this big, so up here, IP bits, the global one, and then we have TCP bits to make it really explicit. And now we're saying IP bits override with the TCP packet, right? So I think that should fix it. Subtle bug. and then we're going to return the global, the bits from the IP packet. Well, streams, people joining. I guess everyone's waking up at 10:40 on a 10:40 PST. Okay, we still have this error. That should have fixed it though. But that's not how code works. You can't just be like, that should have fixed it. I wish it was that easy. TCP bits. Yeah. I mean, at least we can check the sizes now. See what's up. ToString, let's just go into here. All right, so we got IP bits, which are how long? There's the length. We can actually math this out. Do we have a, yeah. Okay, 6. Oh God, it doesn't let me pause a long time. It doesn't like that. Okay, so IP bits. I'm trying to figure out where we're missing bits, basically. We're going back into the debug binary. Seems right. Or at least we got an offset. Yeah, so and then what we're gonna do is say, oh, I see. Yeah. So the 3/20th bit so at position 320 plus 65855 plus the length of the TCP bits. We have an off by 1 error, basically. That's what's going on. But I want to verify it instead of just guess it. Where it at? Here. Oh, also we have, this would do it. Yeah, there. So TCP packet's actually 524,000 bits because it's 65 times 8. The number that was used online is bytes. So we're missing that 8 multiplication. Yeah, and when we created a header for this, right here, TCP packet size. Yeah, this is gnarly. So we have a conversion here we got to catch. Let's remove bits per byte and just say TCP packet size. Keep it simple. That's gnarly. So bits per byte, we can remove that. We don't need that. We're just using purely bits representation. So no wonder we had it wasn't off by 1 error, it was an off by 500,000 error, which would cause a problem. So I think we've caught it now, technically. Let's see. Yep, so we caught it. Now we've just got an off by 1 here. It should actually be the 321st bit, probably. Unless I'm counting wrong, I'm kind of guessing here, but I know that roughly this bit should be set. Let's take a look. So at least we fixed the other problem. That off by 1 bit is now better. So we're in here. Yep. You can see our bits. Just copy them. Cool. Copy. All right. So 320. Oh, we're gonna have the same thing we already fixed before. Sup, Shadiel? Nice to see you in the chat. Yeah, long time no chat. Things are going well, dude. We're just chilling. We're implementing. I'm trying to remember even what we're doing right now. we're debugging binary. Uh, we're about to build a Wi-Fi driver in the next couple hours. Things are great. This chat's bumping. It's pumped up to 5. It's pretty cool. It's nice to see folks. For those who don't know, Jadiel's OG met at Carnegie Mellon. So, all right. So I think we have the same offset thing we did before, which is we want to begin at 320. Yep. But something seems odd here. So go to the beginning, 320 puts us here. And then there's like nothing for a long ass time, which I don't like. You can see the payload, these ones and zeros. This represents the word hello here. And then you can see, well, actually, this makes a lot of sense. Because here's the beginning of our header. Oh yeah, this actually, yeah, this makes sense. So 320 puts us here. And then we're going to say 32 there, 31 there. Yeah, that's correct. So there's 320 zeros now at the beginning. This is because this is supposed to be the IP address, but we've just made the IP address 0, which means we have a bunch of zeros. And then what's going to happen, so you can count it perfectly. 320 bits for the IP puts us, I'm pointing, but you can't see it, puts us where my cursor is, just next to my face. And then we're going to move 32. And then 31, that puts us on the first one, which is the SYN bit for the TCP handshake. And we should move 32 more. Now we're at the next one, which is the ACK bit, which is covered by my face, apologies. And then we move 192, and we're into the payload, where all these ones and zeros are. So this is right. Basically, my test is dumb. Like, the test is incorrect, because we're not starting a SYN bit immediately in the header. It's going to be 320 plus 32 plus 31, I believe. Something like that. And we can check it here manually. 320, 32, 31. Yeah. So let's double check. Yep. Cool. Test pass. So we've done binary encoding of TCP packets and IP packets. I think we're done the binary part now, which good riddance. We're not coming back to this for a while. I say as we probably will, but no, offsets are right. We fixed the things. We've got all these offsets. Oh, that was fun. So now we've got this bits. Now we can finally get back into the stuff I wanted to do. It was just like, oh, we'll just quickly do this, and then just boom, 2 hours just in the weeds. Yeah. So let's commit it. Got status. Cool. It's TLDR for if you just joined in the last couple minutes and you're like, what did we just do? The stream has been going for 2 hours. Surely Kyle did a lot of things. And I will be like, aha, but I have not. I have encoded these two structures in binary. TCP, this packet, or IPv6 packet, and this TCP packet. So writing this logic took a couple hours. Refreshing on binary. Once you got it, it's simple, but alas, that is how everything is once you've done it before. Everything is simple after it's been done. So now we have a send SYN packet. We have 2 bits. This is pretty good. We could like wrap this up a little bit more, but I think this is clear how it's written. And now what we need to do is write to a file. This is where it's going to start becoming a driver thing. So for context, we're using Ubuntu. For context is on Ubuntu or any Linux machine, you can see all of your processes running in a directory structure by going into ls/proc right here. And you can open up any single process, like say 1034, and you could see all the stuff your process is using. So for example, this process has file descriptors. That's the FD directory. So you can go into FD. You can see the file descriptors with even more detail. So these are like sockets. So basically, when you're using pipes and sockets and you're communicating between processes on your computer, your program that you're using is actually just writing files into this /process directory. So it's like, it's not just magically sending data to another process. Like, it's just logging it here. And so we're going to do the same thing. We're going to make /dev/proc. I talked about this in the last stream, but basically we don't want to goof up the process directory. Like we don't want to take up a process ID and then like break it and something. So we're going to use /dev/proc. Yeah, and then we have a folder here, 1, 2, 3, 4, 5. Our process is going to be ID 1, 2, 3, 4, 5. The server is going to have its own ID, but basically we're going to have these like file descriptors for sockets, which are going to be like, if we're doing it really formal, we're going to have like port numbers and everything. And then, but essentially the client is going to write files and the server is going to read files, and that's how you do file sockets. So in this stream, for the next, I guess, until the end of this stream, we're going to implement file sockets, and then we're going to build hardware using a Raspberry Pi that actually reads the file from the file sockets and then sends it over sound, like Morse code. So we're a couple pieces away. We've almost fully implemented like bidirectional, or at least unidirectional communication from scratch. So, and for context, those just joining, all this is written from basically scratch. I mean, we're using libraries. I'm using a computer, so and technically I'm using the internet to stream this. So we're not doing it purely from scratch, but you get the picture. Anyway, we need to think of, let's see if we can shotgun. Now that we're out of the binary stuff, I think we can be faster at implementing a driver. Essentially, we need to think here, like, I'm just looking at how other processes do this. Maybe I could read about it a bit to get some Unix. Yeah, runtime. So it's a fake file system that has like stuff about your programs running. I'm trying to follow the design standards. Because like technically if we follow these rules, we could just ship something. File descriptors. Boom, see that? So TCP sockets are stored for IPv6 in procnet TCP6. So we can actually go look at our processes that are running. And we can see if they're using internet. So this process, for example, isn't using the internet. It doesn't have a TCP file. I wonder actually what process 1034 is. Is there a way to see what 1034 is? Yeah. So let's get info about this process. 1034. Hub proxy. So it's listening, it's a local thing, it's a daemon or something. But yeah, basically this, so for context, we went into the process table, we were like, hey, this thing's running, it doesn't look like it's using the internet. And we're like, what is it? And it's like some sort of thing. Hub proxy? I can look up what this is. Cloud Foundations, VPN thingy-mabob. Well, it should be super funny if it's like a virus and I just have some like keylogger running on my machine. HTTPS upgrade proxy. Cloud Foundations. Anyway, we don't have to rabbit hole it too deep, but basically, maybe we'll do it for one more just because it's kind of fun. Let's go into this one. I want to see if I can find one with TCP. Actually, I should be able to recursively search a directory. Yeah. Okay, so our starting directory is /proc. And then we're going to look for directories that contain TCP. Do we have any? Maybe it's named differently. Oh, yeah. Sudo. Maybe, oh, it's going to have, it's within another subdirectory, right? I think we were just looking at this. It's in net/TCP. So I was searching in the wrong place. There. So here's a bunch of processes using that have basically file sockets connected to network drivers. Let's just look at one, just kind of for lulz. Yeah, we're in here. We got wireless. We got routes. So we can go look at like so what is this process? 4969. And 4969 is, what is this? What is this process? It's our code server. It's our I think this is our VS Code server. Is it? We'll just look at the README. Yeah, it's our VS Code server. We just accidentally found the VS Code server that we're currently using. So for context, I'm using this tool called Brev. We're like connected to I'm connected to a remote instance. It just sets everything up for you. Makes it easy to do like local cloud dev. It feels local. But that's neat because basically we were just like scanning. We saw something's using IPv6 and it's our VS Code server. That's how we're connected to this remote dev machine, right? And we can click in, you can see logs. So anyway, we're going to be doing that. We're doing the same thing. We're going to have, so we've got dev proc, say we've got a process ID. I'll make a example, sudo make dir example. And in here, we're going to do make dir net. We're going to make a net folder. And then in here, we're going to have TCP6, because that's where we want to write packets to. Come on. I want to look inside here a bit and see how it's done. So I imagine how packets are read and wrote is probably using like not just like chunky files with binary. Like it's probably stored in like, I don't know. There's more and more rules for how to organize this stuff at a lower level. So we can read a bit about it. We can also just implement it the way we want. Like we don't have to follow those rules to say we've done the internet. But I think it's more just like valuable to understand like how are people doing this typically. So we're at the data link layer and the network layer. So IP. And let's see. Oh. Yeah. Then physical layer. Basically, in the operating system, like, I'm not too worried about it. We need to have some design that's not stupid. But essentially, what I want to do just for simplicity is a first come, first serve, like a queue. And I want to write packets. Each has their own file. And I want to label them based on timestamp. That's what I want to do. Keep it nice and simple. So yeah, I'm trying to think if that could backfire. There's some speed issues with that. Like you could have a race condition, but like I'm not too worried about the like TCP handles the handshake process. So like if the order is wrong, the whole point of TCP is to handle that problem. But I basically just don't want to deal with like storing a bunch of crap in one file and doing like file read write complexity. I rather have like, I guess, I don't know, let me see here. I guess, yeah, I'm basically trying to think of like what interface do we want. So we want to do, let's design it. I guess, what is this, a packet reader, packet writer? Yeah. Check to make sure. So I've got a roommate moving out, so I need to. We're heading back to Mexico in what is it, tomorrow? I think I'm going to Mexico on Tuesday. I can't really remember. I think in like 2 days, and then I'm going to Canada, so that's gonna be fun. Uh, yeah, back to the fun. Oh, where did all these S's come from? The heck? That's better. Let me think here. So, hmm. So we're gonna have two things. We're gonna have the driver just reads packets, and is gonna send them over the Raspberry Pi. And then the second thing we have is this packet read writer that's part of our main library here, which will, I guess, just kind of get any of the packets. We'll decide what we do with them. Like, so we can send a packet like this. What does sending a packet mean? It just means writing a file, I guess. And then check for, so maybe what I'm gonna try and do is see how would I use a library here. And then we'll define the interface like that, as one does. So this is gonna read, okay. So yeah. I'm gonna call it TCP packet read writer. And what it's gonna do is it's gonna read it's just gonna return whatever TCP packets are sitting on the file system. Yeah, that's easy, nice and simple. So what's gonna happen here is we're gonna have logic like our library here will have a, I don't know, self packet like that. So we got our packet interface, and then packet interface write, we're gonna write bits. Nice and easy. I guess it's technically IP packets stored in the file system. So it's IP packet read writer. Yeah. For packet and packets. What we're going to want to do is we can't just check if it's sequence or ACK bit because they're being read as IP packets. We have to cast them to IPv6 or TCP packets. Cool. Yeah, read TCP. Just add a function in here. We have this read writer. It's kind of shitty. So like, it's technically writing IP packets, but it's gonna connect, like the things it's returning is a TCP packet for the sake of our upstream library. So technically it's a TCP packet reader and writer, but everything on the file system is just gonna be an IP packet. All right, I think we've decided on that. And now we can just call it write and read. We don't need to call everything TCP because we've already named it that. So it's implied. Yeah. So this is pretty simple now. We're just literally like read if sequence is 0 and ACK is 0. found we could just do this. Got sin equals easy. It's automatically going to get set to true if it's found. Check for sin packet. And then false. Yeah, nice and easy. And check for sin ack is going to be the same. I'm going to read packets, same logic for all this. So read packets, except now we're looking for ack equals 1. Yeah. And then we could simplify our logic here. Nice. I love when logic simplifies. And then check for act packet, exact same thing. We could probably wrap this in a smaller function. Keeping it here for now, just because it's like, it's nice and clean, but technically this is screaming to me that it should be a smaller function because we have like the exact same loop in checks. So we could just put that into a utility function and have better error handling on it. We're kind of in the flow now. For act packet, we're gonna have the same thing, clean. Nice. Yeah. So we have the packet listener is nice and simple. Yeah. And then what are these? Those are the check functions. See, there's some duplicate code, but again, it's simple enough that kind of like willing to have it. Yeah. Because yeah, my brain's just like refactor. No, Kyle, not yet. Okay, so how about sending? Well, south.packet interface dot write. Oh yeah, so for send, it's gonna be this thing. We already wrote this above. So an ack packet. Now we gotta remember what this is gonna look like. So what is an ack packet? I think it's indicating that I've sent a packet and received a packet. So it should be 1-1, but I want to double check. Oh, my audio is low. Thanks for the heads up. You can crank it up. There. Maybe that's better. Hopefully I'm not blasting whoever's in here now. Yeah, so ack is 1-1. Yeah, nice and easy. Thanks for the feedback on the audio. Appreciate that. Okay, so send synac. So basically we're just writing some of these packets. All that differs here is the sequence and acknowledgement number. We've got these lower level libraries we've made, so it's pretty straightforward. Synac. So synac's going to be 0 and 1. Yeah. And then ACK is 1, 1. It's the exact same writing logic for each of these. Gonna erase payload. And then data packet, we'll just get here a bit later, but it's gonna be the same. It's gonna be the same thing. So it'll be like initialize. It's gonna be roughly like this. Initialize a TCP packet. Sequence is gonna be equal to bits received, or bits sent. ACK is gonna be self bits received. And then we're gonna write the packet with some data. The payload is gonna be send data packet. We actually need to send data. Can't just have nothing. We're gonna send data, and then we're gonna increment how much bits we've sent, basically. That's pretty straightforward. This should be a bit string, technically. So basically, we don't have to implement this function yet, because like I just want to get the handshake data sent to say that we're ready to send a data payload, and then implementing this is very simple. Let's see. Cool. It's being messaged. Yeah, so how this is gonna run, for context, is maybe I can do a quick run through. So here's the code, like the high level. We're gonna have a Python program that runs this function server, and we've implemented all these libraries. So basically a server is just gonna run listen and then receive data. And then the client is gonna run open, and then if it opens, it's gonna be able to send data. So as an application, this would be like a Python library where you could just literally put IP and port, just like you would do for a Python socket library. And then what we did is we went under the hood and we were like, how do we implement this? Well, we need to do a TCP handshake. So basically, to answer your question, it's a Python library, but we're drilling down underneath implementing, like, okay, here's the handshake. We've implemented the handshake, and now what we got to do is like read a packet from a file system, which will, like, now we're doing the under the hood networking, and we're about to implement the read and write function, and then we implemented a bunch of stuff to encode packets in binary and write it on the file system. So but yeah, in the end, this is basically going to be like Python file socket library. It could be any language. We just picked Python because it's like easy to work with. Yeah. So let me see here. TCP. All right, so we got these checks. Yep. Yeah, so I guess we just got to do a read write now. So writing should be pretty easy. We're given a packet. Right? We already wrote this function to convert a packet to bits. So we did all that work. That's to convert TCP, that's to convert an IP packet to bits. We did all the offsets. We spent the first 2 hours of the stream just getting offsets right. But because we did that, it's super easy to implement this now because we just need to look at like, well, how do you do a file write? Should be pretty easy. Let's see. W3 school. So it's something like that. We need to figure out a naming scheme for files so we're not overriding, but Unix timestamps are cool, except it's easy to have duplicates. Maybe there's a way to be more granular. Yeah, like this. Nanoseconds, yeah. So then it's like having a conflict would require making 2 writes in a nanosecond, except Python executes sequentially, so having that happen would require 2 instructions to run in the same nanosecond, which is virtually impossible because an instruction's a clock cycle, and a clock cycle takes at least a nanosecond. So, yeah. So there's like basically no way 2 executions would have the same ID. So I think nanosecond naming is probably all right. Let's see. We can print it though just to see. But it's going to be like this. Close the file handle. I think it should just be that simple, except now we obviously need to have like a path. We will force it to be in dev proc. Again, we're using dev/proc because typically files are stored in /proc or processes, and all their file descriptors and everything that a process uses is stored in /proc. So we don't want to interfere with that with a toy project. So we're going to put it in dev/proc, which has a couple programs that a couple IDs we've put here. We can dynamically change PIDs and stuff soon, but for now, let's just put it in like, let me think how this is going to work. Because right now they're both going to read and write in the same place. Just put it in an example for the second, but once we actually have these running on separate machines, it'll have to be changed. Example net TCP6. Let me rename it to shared because I don't like this naming of example. Cool. We're using shared for now just to be simple, but TCP6, and then we're gonna not put it's not a text file, it's a binary file, so we don't have to name it as an extension, it's just written as a binary file. So shared TCP6, and it'll be like some ID, it'll be written, it's clean. I think that's how we do a write, simple. And then a read, Well, for this, this is just a Python directory read. So read all files. I think list dir makes more sense. Yeah. Yeah, list dir. We could just hijack some of this and mod this code to scan the directory we want. So it's gonna be like, let me see. Yeah, again, our path is, we should probably have this stored as a global now. Packet path. Nice. It's packet path. Do this. Like that. And then, hey Morgan, welcome. Cool. And we're gonna do packet path. We don't need a keyword. We're gonna say for every file, if it's a file, then we're gonna open it. Packet path. We're gonna read it. We don't have to scan for types. We're literally just gonna be like, open the file. That's it. We're gonna get all the content of the file. I mean, we could put like a packet. I assume if it's in this directory, it's a packet essentially. So the whole premise is we'll do a join packet path. Yeah. There's probably a read command, I imagine. I imagine imagine the file would have a read of some sort. See what that looks like though. Yeah, the whole file. That's what I want. Now what we need is a part one. Yeah. So Twitch apparently auto deletes your streams. So I'm going to be putting them all on YouTube today. Thankfully, I have everything downloaded on my computer, but yeah, I didn't realize Twitch auto deletes streams. So part one is from 3 weeks ago, which Twitch removed from the account. So that'll be uploaded. I could actually check what my I'm trying to see like what even my YouTube channel would be that this is on, but I'll basically link to my YouTube channel from the Twitch. It'll be able to find it there. And yeah, part one, pretty much all these parts so far have been 4 hours of just like tinkering around. Part one's a lot of just exploring. So. Okay. All right, so what we got to do here is the file is going to have bits, like zeros and ones. We need to convert that into this thing, TCP packet. We want to return a list of those. And yeah, I mean, that's what we want. So there's going to be a from function essentially for how do we turn bits into this struct. And I guess what I'm trying to ask myself is, do we want to do this for TCP packet or IP packet? I think we'll do it for, like, this reader writer is supposed to return TCP packets. So yeah, I think that should be doable. So what we should have is in here from bits. See what Copilot's trying to generate. It's gonna be like it's actually not bad. It's totally just taking this from GitHub somewhere. And the brutal part of Copilot is it's almost right almost all the time. So you'll start using it and you'll be like, that's slightly off, and it's enough just to confuse the heck out of you. Like for example, if we look at these offsets, this header size is not the case because there's actually going to be, we already wrote up the header size here, which is 320 plus the TCP header size. So it's super confusing that they do that. The TCP header size is 192. So maybe we can, I think it's time to move this up. So reading bits one by one, it would be sequence offset. Maybe in self. Basically, we need to share these constants. Self. Share them, and then index in if assuming we've done all of our constants correctly from before. We're gonna have IP. There should be something up here. Yeah, IPv6 header size. IPv6 header size. Yeah, plus TCP header size plus self dot ACK or sequence offset. Yeah. And ACK offset. Basically, we're just trying to index into where this bit is stored. We have a big string of binary. It's all just zeros and ones everywhere. We need to figure out where is the first bit that we care about. And so the length here, yeah, that's what we want basically. So we want the bit starting at this position up until this position plus 32, because it's 32-bit. Each field is 32 bits. We get those bit ranges, and then we're going to convert it into integers. And then we're going to store it. We actually don't need to do anything with data. Yeah, this is just garbage. It's fun that it recommends code, but it's like usually just like you have to know what you're doing with it. It just makes no sense. I think this is close. Data offset. Yeah. Cool. And then data offset is header plus TCP plus data offset. Yep. And then a number of bits. Just put it all up here. TCP data size is packet size minus header size. But then to do that, we need to know where packet size is stored. Let me see. Where's packet size? Ah, it's right there. So we just put these together. Yeah, I mean, this is being used in 2 places now. Good rule of thumb, if it's used in 2 places, just make it a shared constant. Cool. Data, bits, sequence offset. Nice. Yeah, just return itself. Yeah. So it's kind of like a static function, I guess. We can initialize the struct from a method within the struct. So I think that's a static method, from my understanding. Yeah, good stuff. Is self actually valid? Can you do that? I guess. I don't think we need to return anything, actually. I guess unless we're trying to do like an assignment operator in Python. Cool. But I think we're on the right track. Time for a commit, probably. Or we can do a test. Since I just moved around a bunch of variables, I just want to do the sanity check. that we didn't break our tests. Our simple tests, but they are still tests. Yep, passed. It's a good just sanity check. Main. Push it. It's kind of funny. We just have like libraries and then just like random test functions and then more libraries and like, could definitely clean this up, but later time. So anyway, that's from bits. So assuming that works, we should just be able to do this. Yeah. Easy. That's basically it. So the read function becomes really simple once you have this assister. What's this? You have this help function. Assuming that works, we'll have to test that. But assuming that's right, that's how we read all our packets. And then the write function is pretty straightforward. It's just write the thing. And now these utility functions, the things we're trying to implement in the first place, are just, they're already done, right? Because the logic's pretty simple. It's just read all the packets, check if the things are set how we want. If so, bail. And then we use those to implement a handshake. Here, we've already tested this. So all that's left is to send data. So technically speaking, we should be able to do, we should be able to just run the server and client, and it should just write files and then read them and like work. So I think the next bit is going to be spent just making sure that works. We're going to have a bunch of blockers like file permissions, stuff like that. But I'm going to use the restroom quick, but I'll be back in like 5 minutes. We're back. I got a drink. I also ate a whole bag of chips. It's hard to have foods that aren't like awful on a stream, like ones where you're just crunching. I realized that as I went to a snack cabinet and I was like, what should I eat? I think a banana is one of the few that work. Also, Banana's the name of my company, banana.dev. Check it out. Where were we? We were like trying to build the internet, right? So, no, we just got to run the thing, right? We're basically done. Let's try it. I think we're probably going to spend like 5-10 minutes just like ironing out hella broken stuff. Move that out. Come put it right here. I'll pack it. Put it to bits. Should probably. I really don't like that the class name is TCP packet writer and we're writing an IP packet. Yeah, that's garbage. Naming matters. Yeah, like that. We're just gonna call it packet read writer. If it's not one specific one, it shouldn't be named wrong. But we keep oscillating between names on this. That's because it keeps changing. How would I describe this to like somebody? Well, we're reading and writing packets. That's what we're doing. That's how I'd use it in like English day to day. We can read or write TCP or IP packets. So we're reading TCP, we're writing IP. That's the way I describe it. We haven't implemented the other types. So I think that's the simplest way to, like, it's good to design interfaces that are descriptive with respect to how you actually talk about the thing you're doing. It's really dumb when you're like, oh yes, I would like to write a file using the buffered interface file reader writer. Like, it's like, no, nobody talks like that. What we want to say is like, hey, I would like to write packets using the packet read writer. I'm reading and writing packets. That's what I'm doing. And technically, we could make a reader and a writer separate. The fact that this is kind of a cluster of just garbage is because it's a poorly named utility library thing. Like, it's just a jumble. It may as well just call it utils, but that's even worse. Try not to be completely unhinged here. Yeah. Here it is. Read writer. Now it's very clear. Write IP. Now it's read TCP. Read TCP. So the return is a darn well better return a TCP packet, not an IP. And if I'm writing, you darn well better give me IP packet, not a TCP packet. Just trying to get some, try not to be completely garbage without renaming things. I know it's a hacky MVP, but let's not be trash. Nope. See, the naming is very clear. It's like we are writing this. Do not write anything else. Yep. And then IP packet. Or IP. TCP packet. Consistency. Now, oh, this is kind of nice. We can move all these 2 bits things. I like that. It's nice and simple. Okay, our naming's consistent. We've reduced some duplicate code. I'd say that's an accomplishment. If you can write less code, you're doing well. I guess you're doing well unless you're doing like code golf. There's probably exceptions to that rule, but I think typically if it's the same readability and the same function with less code, that's probably better. Cool. Let's try running it. See what breaks. Permission denied. Hey, what did I say? That's exactly what I said was going to be the problem. How did he know? Well, I know a thing about Ubuntu and Linux. How do I... Oh, that's a pain in the ass, though. That's a pain in the ass. We're gonna mock it in this folder. Yeah. Because I don't wanna, unless there's like an easy way, let's just see. Maybe there's like a one-liner. Yeah, there we go. There is a one-liner. My brain was just like, oh no, that's gonna suck having to do this. Sudo. Oh, I see. Just put it there. Oh, there's a file. We wrote a thing. But didn't work. From bits is missing the argument bits. Well, Can I have a static method in Python? Come on. Wow, you literally define it as static. Makes sense. Yeah, for context, static methods let you, static class methods are methods, i.e. functions, that you call a class without initializing the class as an object. I'll also move this. So we should probably go here and then go lag. Well, bam, static method. Oh, look at that. You can see how it's implemented. Oh, this is amazing grape soda. Damn. 4 grams of sugar. No way. That's bullshit. This must have aspartame in it. Yeah, it says 9% juice, 4 grams of sugar. What's in this? There's no way this is... It's got stevia and syrup. Ugh. But it tastes good, you know. And in the end, that is what will matter for the consumer. Okay, 59. We already did this. Am I naming it wrong? Static method. Oh, well, maybe the problem is because I'm calling it with self, but it's a static method, so it's not supposed to have self. Like those keywords seem to conflict. Yeah, that was it. Oh, but then, yeah, you can't just use self now when there's no self. Okay, well, these are constants, so can I just do class level constant? Maybe. Come on. Yeah, you can do that. Let's see why I'm not. I don't think I'm breaking the law doing this. Oh, Lord. There. Nope. Nice. Does this work now or is it not? Interesting scoping. So now I have to like redeclare the class name. That's kind of ugly. But I guess self. Oh, so can I avoid having to refactor it? Just do that. So that seems to work. So self implies it's the class name. TCP packet. But if you're in a static method, then you have to do it like this. I see. TCP packet. Cool. Quoted. When we gotta initialize it, this feels kind of abstruse way to do things. I'm just building a constructor. Let's just be real here, guys. Come on, that's what's going on. I don't know if this doesn't feel like the right way to make construct an object, but because like, I don't know, I guess, sure, fine. It's just a from method, but, and I guess it makes sense because it's defined within TCP packet, but sure seems just like a separate method. Like it shouldn't be a method. It's not something you perform on the class. I'm not sure how I feel about class methods or static methods. Well, let's run it. You've messed everything up, Kyle. Ah. 3 required positional arguments. Really? I guess you're right. We should have defaults. That's what we need. Well, let's make, yeah, let's just make it default. Starting to hit that time of day where everyone's texting me. Just chuck my phone away. Be gone. Distracting device. I really don't like this. No, we're not doing defaults. It's ugly as shit. If you're initializing a class, if you're initializing this thing, you're providing the required arguments. I really don't want to create a world where we just have like these random values that we don't want. And we're being super explicit here. We're initializing it there. So now at the call site, we don't have to speculate about the values of this object. Whereas here, it's confusing. Okay. Invalid literal for int of base 10. Oh, it's just an empty. Oh yeah, of course it's empty. Actually, no, not of course. Let's check it out. Well, so bits is an empty string. If you call something with an empty string, what do you expect? Oh. Preconditions. It's kind of an aggressive exit, but I mean, it's what we want. We shouldn't be calling shit. Shouldn't be calling shit like this. So Also, the real problem is that the files I'm trying to read don't have content in them. That seems like the issue. I should probably do that. Yeah. See? ¿Todo bien? Yeah, I think that's the problem. String. This is cool. So this caret at is how you represent 0 byte as text. I don't want that. I would like to explicitly store this. Is there 2 file on this? Also, a random tidbit. Today's the Pride Parade. It's kind of cool. I'm in San Francisco, which is like the place to have the Pride Parade. So it's kind of cool. I'll go check it out after. What was I doing? Yeah. So bits.toFile. Whoa, does it? Yo, hold up. Maybe like that. Right, function must be a string, not a byte array. I don't even know where it's failing right now. Yeah, so I get that. Right argument must be a string, not a byte array. But that's the whole thing I'm trying to write. What? Wait. Oh, is it because I didn't delete? Yeah. I mean, obviously I want to write it as a... Now, the whole premise is I'm writing a string. Why would I want to do that? That doesn't make sense. That makes absolutely no sense at all. Test bit array. This is kind of weird because what the library is letting me do and what it says it'll let me do are different. And I do not like this. This isn't the life I signed up for. I mean, I did exactly what it said. I hear birds. Just 2 bits. Oh, it was different. I added a B and it fixed it. Binary mode. Oh, wow. That's exactly what I wanted. I thought W meant right and B meant bright or something. Well, that's quaint. On to the next error. On to the next error. There we go. Yes, quite. Invalid literal for int with base 10. What do you mean? Well, it's an invalid literal because I'm trying to turn it into an integer. That's the whole reason I'm calling this function. Maybe string first? I don't know if that's gonna do it. Seems like a way to mess up. Yeah. Turning it into a string does not fix the problem. Ah, from file. I see. Aha. And then there's a read binary. Yeah. Okay, how does this work? So, all right, we gotta have a handler, and then we initialize a bit array. All right, we already got the file handler. We got the bit array. There. Can I do that? One line? Oh, so I can just do a file. That's pretty Pythonic. If you ask me. it's going to throw an error because it's a bit array. Yeah. Must be a string. I guess that makes sense. Keep writing sax instead of sec. Come on. Come on now. You can do it. You can do it. Seems okay. Let's see what happens if we do this. It's pretty darn obviously a string now. Nah. We're back. We're back with casting issues. Struct. What? Then you read it as base 2. Drank too fast. Oh no. Okay. I kind of like this method. I can grok this. Like I can see this being, it's like, all right, yeah, convert to a string, and then convert to int. Fine. That's okay for me. What do you mean bit array has no attribute? Must be a pretty straightforward way to do this. Can I just like do a string like this? And then just be like, base 2, please? Okay, what is this library? Bit array. Unpack. hot examples, hot Python examples in your area. Oh God, so many ads. Ugh. I feel like ad blocker is not working anymore. I've already disabled ads. Oh, I don't want to unpack into like complex struct. Bit array. Is that even what I want? Let me just double check, like if this even makes sense. Can we avoid doing this? Yeah, I mean we want an integer. Unsigned long. Seems like I want a 32-bit. Unsigned long seems like what I want though. It's a weird library name. The fact it's called struct. I have so much trouble spelling this variable. Every time. Every single time. Alright. Come on. Come on now. Come on, buddy. Bytes like object. It always wants. It's being one of these things where it's like under the hood, it's actually a different type. Man. So I need examples using this. Because we already got it right here. Bit array to integer. I'm using like a different library. That's the problem. All these docs are for like bit array underscore. Looks like they're doing it right in here. Hmm. It looks like it's supposed to support this. That seemed to work. Hmm. Yeah, I did it. I did it. Yeah. This is the way to do it. So it's unpack. Yeah. Man, we tried so many things. We tried so hard and got so far. I think I'm supposed to do, oh yeah, res. Yeah. Sick. Yeah. I think we did it. Oh. Yep, we did it. Oh, we did it. Margaret, get the kids. Oh. Honey, get the kids. We fixed it. It's a miracle. Multi-processing? What? Am I using this library? Oh, I think I am actually. Yeah, I am using it. Aren't I? Aren't I using it? Yes, I am. Cannot mmap a file. The heck? Cannot mmap an empty file. Cannot mmap. What does this even mean? Multi-map? What? Where's this even coming from? In here. Not byte array. Bit array. Ugh. File reading is always a thing that causes some headaches. Oh, I bet you it's this. It's just because I'm not reading binary. Yeah, I have a hunch. Cannot mmap an empty file. Can we just like not do that then? Wow. Yeah. Now it's just like 0. Okay, well, we've just made progress. Oh, we got 1 file. So we've sent a SYN packet. Yep. Good. But we're not reading it. So that tells me we've got, so the server's not listening, right? So it tells me something's wrong here. Yeah, we gotta figure out what's going on. We're stuck in this like check loop here. Yep. And then if we run this again, we're gonna keep hitting this. Yeah, so let's drill in. Read TCP. What are these? Well, obviously, yeah, the values are all arrays. No wonder it's shitting itself. What's going on? This from bits is wrong. We didn't test it. That explains why. That's what you get. Yep. We got there. Aha. Now we're okay. This is good. We're hitting new code paths. It's a good. So wait, where is this? Send to Synac. Ah, we're at the Synac line now. So we're making progress. Yeah, it's pretty good. Let's see.
sending Synac. Now it seems like the client, so who's waiting for Synac? The client's waiting for Synac in the open function. So this is going to keep getting hit. Yeah, so we're failing here. So let's drill in. Same thing we just did. Well, so the problem is that none of the packets in the file system have the ACK set to 1. Well, so the server didn't write it properly by the looks of it. So this is wrong. Let's run this again. This bit is in the right place. That 1 is exactly where it should be. Darn right. But still not working. I have a feeling the reading is wrong. I saw in Stack Overflow there's some notes about how like it adds padding. I'm just trying to think if that wouldn't affect the offset. Still. Like adding zeros to the end doesn't change my life. Doesn't make the world a different place for me. Could it though? Yeah, so we wrote this. And then we're stuck waiting for Synac here. And this is happening because none of the packets have sequence set to 1. And why is that? Well, we know one of them's technically I should see something in here, probably. So like one of these things. Yeah. Is there a 1 in here? There's no 1 in here. So that has no 1s. Does this have any 1s? No, that's a Dana. Yeah, I think we got to test the file read. Let's do it. ACK is 1. Yep. So we're going to write it, and then we're going to do that's what we're trying to do. So I think I just wrote like a test that should pass. By test, I mean like some prints. Yep. Okay, so there's the write. Now we're going to do a read. There should be 1 packet. Where is it? Where is it? Where it at? Yeah. And there's no ACK bit set. So we wrote the file, we read the file, we lost the bit. That's not what we want. That is not what we want. Do we have any 1s in here? There's no 1s. I mean, that's the problem right there. So, okay, so my understanding is write IP isn't putting 1s in the write. Weird. It should be doing that because I told it to. Bits. So here's the bits. We have them now. There's the 1. I think we have a very clear problem. The problem is that I can write a 1-bit to a file, but then when I read the file, the bit is gone. Yeah, like there's just no. Okay, so what's interesting here is are we even reading the same length? Yeah. Five, 2, 3, 8, 9, 6. So that's the length of the five, 2, 3, 8, 9, 6. That's the length of the thing we're reading. What is going on here? Oh, I see. I already have the interpreter open. That just breaks the debugger. So let's look at these bits. And this is 524 600. So we're writing 523,896 bytes or bits. We're reading 523,896, and then we're writing 52,4 600. We're losing bits. That's what that means. But that doesn't make sense because the bits are here. We can see them. And we're doing a file write, and I highly doubt that's failing. And so the problem is in how we're reading it from bits. It's this function. It's gotta be. Right? Are there bits here? And we can check right here if the read's right. The read is incorrect or not. Okay, so here, 524 600. That's correct. So we haven't lost bits, basically. We wrote a file, we've read a file correctly. So the world is not completely deranged. It is us that need to fix our shit. And now, well, I guess the second check. I guess the second check is in this bits variable. Can do a check. There's the 1. It's right there. So 320, 32, 31, and 32. Yep, there it is. It's exactly where we told it to be. Well, that tells me the read logic's wrong. But how? How could the library that I wrote an hour ago be wrong? How could I have made a mistake? Impossible. Could never happen. Unless it did happen. I have a feeling this is wrong. That's 320. That's ooh. This is wrong. It's obviously wrong, because look at, check this out. Pro gamer move. So if I go here, I already know the offset, right? Where is it? So 320, and then we go 32. So now we're skipping the very beginning row. Now we're moving 31, which gets to the end of the seek bit, and then we're gonna move 32 to get to the end of the ACK bit. And there's the 1. Now in the logic, we're doing 320, and then we're doing 192, which puts us here. We're skipping like 100 bits. The problem is that, where is it? We're offsetting the TCP header size when the sequence and ACK are in the header, not in the data portion. So, no shit. Like, this shouldn't exist, basically. I don't see why. I don't know why that exists in the first place. Gnarly. I think we're good now. Because, okay, as we write some stuff. Whoop, whoop. And then we're gonna read. Yeah. TCP header size. That's right. But sequence offset. Sequence offset should just be 320 plus 32 plus 31. So our sequence offset is so up to 83, yeah. And then ACK offset yep. $447. There it is. There's that one. We caught it. Gnarly. We caught it. We're reeling it in. It's a big one. Ooh, typo. A typo. Ooh, Okay, we're searching for the word got everywhere. We're searching for the word get. Good. Get good. I think we just like casually fixed that. It's a good thing we spent some time writing these early abstractions well. Could you imagine how shitty this would be without? Like, our lives would suck if we didn't have this. Whoa, we did it. Oh, we did it. We did it. Oh, God. Wow. Wow. Look at that. Well, we just did we unblocked one little thing. I thought we were going to get stuck a bit more, but we ironed out one of the things that was stopping us. And turns out when you remove the things that stop you, it doesn't stop you anymore. One thing that's weird here is the order of the prints. I don't see how they're printing at the order here is wrong, basically. But it could just be because they're printing at the wrong times. But could also mean there's a problem. Could mean many things. But one thing is true, and that is that we have created a handshake thing for something. We've done a thing. That is true. We've done stuff. Basically, it's not as crazy as I wanted it to sound, but I'm just saying we've successfully accomplished things in the span of these almost 5 hours. I want to clean this up though, and I want to figure out. Yeah, I can see a couple weird things here. So ACK packet. So firstly, we're spelling this wrong. That's a synac. Got synac packet. Got synac. So basically, there's no way that it should be syn, ack, and then synac. It should be syn, synac, ack. Oh, but it's sending. How's this working? So I think what we need are we need confirmations when we've received. So sending syn packet. It could also just be the ordering here. So like, yep. All right, just try it again. Just see what happens. That doesn't make sense. It can't possibly. The only way for send act packet, there's got to be a bug here. Because we've done okay, syn packet, syn send, right? False. Checking for syn act packet. The only way for act to get called before the other server said, before this got printed, is for check for synac to return true before it should. Which means that this check sequence, this passes somehow. Which means that somebody wrote this packet. What's the synac packet look like? Send synac. Yeah. Make sure we're getting these state. I have a feeling we have a bug in the this logic. Yeah. So 0, 0, 0, 1, 1, 1. There it is, 0, 1. And then somehow this are these separate processes? You know what? This is like
super easy for this to cause printing race conditions because of like timers and shit. So the way we can really check is by yeah, I mean like there's just so easy for this to print in the wrong order. We could do timestamps if we want to. You can do a log. Let's just do a quick. We gotta clean this up, these prints a little bit. Basically, that has to be yeah, so format is a string operation, so we just need to replace print with log, basically. What I'm trying to do is if we print timestamps, we can see what's screwing up. Let's just see if this is working first. Maybe I've got a typo. Yep. Forgot Python's time.time. Yeah. We should probably already be able to see it. I mean, it looks wrong. Yeah, I mean, this is nice to have because it's just clarified that we've definitely got something wrong here. It's also less words to write log. Well, not less words, less letters. For the people who would be like, actually, it's less. Let's see. Why would that be happening? Or how could it be happening, rather? Yeah, there's no... I'm trying to... Oh, wait, is it because... It's because I literally wrote the syntax packet before we called the state machine. Watch this. I bet you it is. I bet you it's because we literally write a state file before we call the thing. You know, I have a feeling that would cause a problem, writing a syntax packet. Yeah. Classic. Look at that. Dude, isn't this like just sick? Look at this shit. Come on.
How cool is this? Just watch it again. This makes all the hard work worth it when you can see console output like this. Look at it, it's waiting. Oh, got it. Oh, wait. Boom, got internet. Send data. Receive connection. Then we're able to like send data packets. And I think there's one more thing I want to make it work, which is actually doing this data part, the send and receive. Because right now we're just like sending shit. I would like to do receive logic. Basically, send and receive should be looking at the ACK bits. Like it shouldn't be just sending is fine, but receiving shouldn't be receiving just any old packet. It should be receiving packets in order. Because what I want to do next is send. I want to break down a payload into like chunks and then send that and make sure it's received in order. Because then I would be like, we've actually got the handshake. And then what we can do is we could break down arbitrary files into payloads, like a JPEG, whatever, a video, and we can transfer that. So I want to make that work. First, let's commit this. Although we have all these files, it's just like, it works. Or so what is it? We hand rolled our own file sockets. And we've got shit working. Got shit working, dude. That's what matters. Yeah, I think there's a bit more I want to do to refine this. I want to like push through so that we, on the next stream, are just like pure hardware, can do some awesome shit. Also, I have carrots still, so I'm going to eat a couple of carrots. Yeah. Just marveling a little bit at it's messy, but like I like what we've got here. Probably by end of this stream I'm gonna clean some of this up. Like it might be worth just being like, all right, just put it in a different file, like for love of God. Because now that we're getting to 300 plus lines, starts being worth changing stuff around. This is also like pretty dense code. These aren't like auxiliary things. All this shit is like state machines, bitwise logic. Like it's all, every line's important. If you delete one line, nothing works basically. So probably best we can do is just move files. So look through this thought. Okay, so the sending part. Send data. What we want to do. Okay, so data is a Send data packet. I think we have a send function, right? Here. Yeah, so we need to implement this, which is split. This is the logic, the splitting stuff. Send data packet should be very simple. Or should it? So I guess what we can do here is I'm trying to figure out where to count the number of bits sent. I think the split part is where it matters. Like the packet should just be doing write. We shouldn't have bits to send. We shouldn't be incrementing shit here. Yeah, because that's ugly, basically. Like the core reason is that's ugly. All right, so we do a split. We tag things with the right numbers, and then we send. Each packet gets sent. It's just a wrapper. We don't even need this payload thing. Yep. And then we can write it to a file. Very simple. I would love to do like 20 minutes of just make this as short as possible. It'd kind of be fun. Like a code golf and be like, I implemented TCP IP in like 100 lines or some shit. Because we can definitely prune out some of this logic. But okay, for now, send is simple. It's like this logic's all done. Sending data packets is done. The split logic, what do we need to do in split? Okay, we got a payload. Is it max payload? TCP data size. So how does this work? So sequence is equal to the, I believe it's the number of bits sent in total. Yeah. 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 That makes sense. So
Bet you there's a yeah. Split using a delimiter. I want to split by size though. I don't want to split by I want to make it chunks. I want to make it chunky. Could use range based. Yeah, we could do like this slices. Sounds like a while loop. It also sounds like something that's been done before, so I shouldn't be implementing it. This is definitely an interview question. Like this is like whiteboard 101 first leak code type thing. I can feel it, I can taste it. And there's definitely a one-liner of how to do this. It's going to increment by number of chunks. I love this one. I love this approach. This is super clean. Yeah. So take a slice, which is the from I to I plus memory size for every starting position of 0 up until you can't anymore, where you increment by the size. So your first chunk, if it's chunks of 10, you're going to get 0 to 10. Then you're going to increment to index 10. You're going to get 10 to 20, not including 20th element. Yeah, this is super slick. Nice. I like that. Cool thing about Python is you can like do stuff in one line. It's definitely great for this type of coding, like just making stuff work. When you don't care about scaling it, you're just like, it just needs to work. And when you want to not scare away people who are new to coding. Cool. So, all right, how's this gonna work? Chunks. I'm gonna call it chunks. No, I didn't even get to finish writing it.
Copilot's like, is this what you mean? Is this what you want? I'm like, yeah, that's it, bro. But come on, I can code. I can still code. I know what I'm doing. Don't have to take the glory. I was gonna write this ranged loop. I don't know, we could simplify that. How do you like this? GitHub. I'll make it easier. Yeah, so we're just gonna up to size for each element, 0 until length. Thick. And that honestly should be it. It doesn't feel like that much, but yeah. That's it. And then we're gonna make packets. We're gonna make packets with everything we need. Yeah, and how we're gonna do that is like this. I also have to figure out where I'm living today. I think I'm staying at a hostel. Yeah. It's just like on my mind. It's one of those things that creeps onto your mind when the day passes by. You're like, I gotta sleep. I gotta sleep indoors. If I'm sleeping outside, that's gonna suck. It gets pretty cold here in San Francisco. Or chonk in chonks. Chonk. Yeah. Easy. We're just gonna use a couple of these variables that have been defined in the class. Yeah. So source IP, destination, bits sent, bits received, and then down here, I guess for each cycle we're gonna do. See, this is where this is where it's weird, because technically, it's easy to lose track. I think we should be incrementing bits sent here. Yep. That should do it. Just a sanity check. So we're gonna start, first time we send something, we split it. Say it's 100 bits long. Originally we're gonna have sent 1 bit because of the synac, or no, we're gonna have sent like 2, I think. Yeah. So sent is 2 because we've sent syn, we've sent ac. And then say we send chunks in 10. We're going to send, the first one's going to be bit sent as 2. And then we're going to increment by 10, so it's 12. And then the next one we're going to send seek as 12. That works. And then when we get to the last one, we're going to send it, say there's 5 bits. Say it was like 95%. We'll get there. It's going to be 2 plus, this last one's 5. So it's going to be total, it'll be 92 plus 5, which will be 97. We'll increment here, we'll bail, we won't continue. So the last seek we will send is 92, but this will now be 97. So on the next packet we send, it would be 97. But I think when we close the connection, we'll just reset these numbers. So easy money. I think that's it. Okay, so split. Split. What else we gotta do? I think we did it, honestly. Send data packet. We don't even need a send data packet anymore. Yeah, that explains why we didn't, this part was confusing. We don't need it anymore, that's why it's confusing. Like we're just sending a packet. We don't need this send data packet. Yeah, the split function does what we want. Cool. Now what? Well, I think when we call send, yeah. Bit array. We're gonna get stuck back in having to figure out how to convert strings to binary. I think we've done that enough today. We spent like at least 2 hours doing that. Trying to think if that's gonna do, it's gonna do something weird for us. So, nah, it should be okay. Okie dokie. I'm gonna look it up. Bitstream. Didn't I already do this? I'm like pretty sure. I'm pretty sure I solved this.
Where was it? I already did this. Where 2 bits. Yeah. Here. Yeah. That's it. So in the send part, here, we're gonna do bits. Equals binary of int from bytes of payload dot encode big endian. We're gonna split bits into packets. What is this class again? This is like a connection of sorts. TCP connection. Let's go back down here and do some testing. Just mock this. Yep. Yeah. Go in here. Boom. There's the bits. We did it. And then split. All right, we've split it into packets. It's only one packet. Right, you can see it. And then for each packet, we're just gonna write it. A bam. Oh. Simple as. I think that's effectively all we need. Yeah. That's pretty much it. We wrote the file. Let's go take a look. I think that's pretty cool, if you ask me. We can also, let's take a look at the file specs. How big is this payload? 65. Oh yeah, it should be 65,575. Well, it's 65,400 plus probably some bytes to, like, there's probably some overhead for a file. Like a file probably can't be 0. It probably has like a descriptor, like the file name, which the file name is a number of integers, which are ASCII, which each represent some number of bits. So that's probably what that is. And well, what else? What else do we need? Well, that's like surprisingly it, I think. I think in the in any of the send functions, yeah, bits sent. We can simplify this quite a lot. because we could just put the increment, like we could make bit sent always be sequence and ACK. We could bundle that into like a line. We can compress a lot of these lines into simple little things, but what matters right now is when we do send ACK, all that matters is that like when we're sending bits, we need to increment the send function. I don't know what else to do. I think we did it. Well, let's test it because it's gonna be broken as shit probably. Let's do end to end. Yeah. Yeah, so I think the test code is still there, which will goof us. But if we just send it, yeah, that. Yeah, there's the file. We sent a payload. Could try splitting. So let me check. How big? I think it's 32 bits. Where is it? Come on. Imagine it's like 8. Imagine it's a byte. All right, so what happens if we do Yeah, let's see if this, let's just make sure this gets split up.
Nice, turned into 42 packets. And then each packet is a wha-bam. Nice. Got an error, that's good. So it means we've tested it. Yeah, what's wrong with this? Well, two bits. And then here, I think I fixed this as well. The TCP header size being too big. Pretty sure we had exactly this. Let's try running it again, just curious. I wonder if I broke my earlier tests. I bet you these are failing now. What did I do wrong? Oh, but they're passing here. So the problem is I think in the split function, because TCP data size. Yeah. Well, because we're getting down to here, we're sending. And to send, we do 2 bits. IP packet, 2 bits. We already fixed that. Like we already tested this function, so we know it, at least in this case, works. I think the
I guess am I sending in too much string data? Like maybe we could check. I could go from bytes. Okay, let me see. In here. Yeah. I think right here, understanding how big the payload, each of the payloads are, would be helpful. Yeah, so in packets, here's the first one. There's the data. Now, how big is this? Are they gonna let me see it all? Okay. How big is it? 6.5. Oh, this is like way bigger than the allowed limit for number of bits in a packet. Like this is way thicker. We allow 65,000 times 8, which is like less than 700K. And if I try to move 700K characters through this file, like I get like a tenth of the way. So this file is like way thicker, which means the split function is not splitting into chunks of the size that I want. Yeah, it's 524. But I bet it's doing, let me check, what's it splitting here? Let's check the payload. I see it's skipping the debug. Cool, let's go here. How about here? Cool. Okay, let's copy, put it there. Yeah, this is just way longer.
if I save this even as like prefix. Yeah, it's 524, but it's literally characters. Well, that's actually weird. The file seems like... Oh, but that's bytes. Yeah, it's writing each thing as a byte. Okay, so hey, welcome to the live stream. So we got somebody new joined. Yeah, right now we're just we're finishing up this current stream pretty soon. I think just final touch-ups and trying to send like larger payloads. And then I need to be sharing a lot of this on YouTube. If you're interested where other content is, I'm just getting used to Twitch. So I'll be posting stuff on YouTube because I realize Twitch deletes videos. So. Cool, so this is gonna be weird. So like, all right, what do we know right now? Well, this prefix file seems reasonably sized. Oh, good question. You're asking how are we making the internet? Well, we're gonna be doing, well, we've made a lot of progress in the last few weeks. Basically, the internet is a bunch of protocols defined by the military. We're implementing those protocols like TCP, IP. We're building stuff like file sockets, all the things you need to send data between processes in a computer. And then we're going to build a Wi-Fi device using a Raspberry Pi that uses Morse code to send encoded packets, like IP packets, to another device that will be listening for it. And what we're going to do is send text or an image from an application. So like if you look actually in the code, I can just show you what we've got. In the code level, we've got very similar interface to what you'd have in like Python when you're doing WebSockets. Yeah, I'm making a private internet system, exactly. Like my own local, I think a better way to phrase like local area network, like a LAN. And technically I could interface it with anything else, but like I'll be able to connect to another device, which would count. And if I connect it to like a local internet provider, then I would be public, but I don't think we're gonna do that. But the goal here is we have this code for server and client. We can open a connection. We've gotten that far. We're trying to figure out how to send larger data payloads. But yeah, it's super cool. And yeah, if you're interested, every Sunday we'll be doing this, or pretty much every Sunday I'm going to try and do a stream. Been doing it for about 3 weeks now. And next Sunday I have to buy some hardware, and we'll be doing the hardware level. But I haven't done this before, so we're just kind of learning as we go. Yeah, and if you have any suggestions for cool projects too, please let me know, because my goal for this channel is to just build really cool things
and learn as we go. So if we get stuck, we just kind of figure out how to do it together and like ask other people for help and just like figure it out. So there's a lot of different neat projects we could build, but I imagine this one's about a couple weeks out from having like a finished project. So anyway, I'll jump back in. I think the goal here is if we finish debugging this this one part we're at, which is sending data payload, again to restate the issue, we've got we get an error saying that we're sending too much data in one packet. Like we've defined a limit to a packet size, and then we have an overload. And yeah, technically with the device we're building, we would be able to send info. Well, since I'm doing like a Morse code adapter, like really simple, I can actually think about making it a longer range system. We can decide how long range of a system we want to make. So I think the minimum version is going to be something that just runs in the house, so like home Wi-Fi. But I think if you wanted to have like a radio tower and like broadcast signals, you could technically you could have like a local internet in like a village or something if you wanted to really build it. Like, but then you're doing a signal problem, so they're kind of like two separate problems. Yeah, so exactly, like, so there's like building internet is one thing, like just being able to implement the internet, but then building long range signal is like a physics, like it's a very different, it's part of the internet, but it's like they're two separate things. So I think the goal for me is to have like a basic functioning thing of the internet that works. And then I think it'd be cool to see like what are the big limiters. Like what would we do next? Yeah. So, okay, let me see here. We split. All right, so we've split it up. When we write a packet, what we know is the packets end up being roughly the size we expect, which are 524 kilobytes. But the weird thing is this bit string boundary error we get from here. Let's look again at the amount of data we have once we hit this call. Right, so B data. All right, we got this data here. Let me check this a little bit more. Oh, this one must be fine. Yeah, so that one's okay. Okay, so I think we have a really simple way I can hack around this, basically, to work for the moment, which is just split stuff into 10 times smaller pieces, and then increment by the payload size. Yeah, like this is literally, I just want to see if this fixes it, if I make it smaller. Float object cannot be interpreted as an integer. Okay, so we'll just do cast. This is me just trying to figure out if the off by one, if it's like an off by one error or if we're like way off. Cool, we fixed it. So I think we have an off by one error. We're able to send packets now. For context, we're not sending them over Wi-Fi yet. We're sending them through file sockets. So just like how on Linux, you can see here in our file system, we've got all the packets we're sending on the file system, and then we're going to send these over Wi-Fi. I like the robot idea. Robotics is actually what I studied a long time ago. So, or not too long ago, but a few years. So do you mean like a robot controlling a game, like a Let's Play? Also, this is cool. It's funny that this fixed it. I've probably got it's literally off by like 2 bits or something, and it's causing this problem. Let me try it with divided by 2. Oh, divided by 2 doesn't work. So, so is it divided by 8? Oh, watch this. I bet you that'll fix it. So 8 fixes it, 2 does not. How about 7? If 7 fails, then I bet you I know the problem. That didn't fix it. Okay, so then I'm not sure. I thought it was that we were using bytes instead of bits. Or actually, wait, no, that does make sense. Literally, okay, so 7 didn't work. Okay, let me try this again. So if I divide by 7, it's too big. But if I divide by 8, it works. So that tells me that each character, so each character is a byte. So we have to actually divide by the payload size by 8. And it's telling me that this payload size here, let me see. Interesting. It's telling me that this packet size was 8. Data size, there, is defined as packet size minus header, but this is multiplied by 8. So we actually got to divide because the length of strings in Python are stored as bytes. And those are 8 bits each. So when we're doing bit calculations, we multiply by 8, but when we're actually doing string measurements, we divide by 8 to make it number of bytes times 8 bits per byte. Weird. Okay. Making a robot which uses walk. I like this idea because it's like, well, because there's 2 really hard parts. So there's there's a bunch of challenges here. So there's the something that learns from walkthroughs on the internet. That's one thing, which is that's a hard challenge. Then there's make a robot that people can remote control, which is like a physical challenge, like just build like a RuneScape bot that's analog, so like controlled using people on Twitch. And then there's and then like actually doing well in a game is like a whole separate bot, right? Got it. This would be an app. Yeah. Okay, that makes sense. It's like a reinforcement learning. That is kind of cool, actually. I like the idea of like a robot that learns to speedrun by watching the internet. Yeah, like you basically give it a game and you tell it like go watch all the best YouTubers on this game and then figure out how to play it. Well, there's packets. Very cool. We're now sending data. We figured out, let me save this and actually put a comment because that was a weird bug. So this payload's a string. Yeah, that makes sense. I think we're getting pretty close to being able to do the hardware part. I think the next step would be, okay, so again, like let me clean this up. Delete this large payload test. So we fixed a bug, and now if I run this, we can see it open a file socket connection. So sending a packet, waiting for the server. Okay, the server responded, we sent the response. Now it's sending data, and then it closes connection. Cool. So let me verify on here on the send. The send is now splitting up the data into chunks. And then receive, we technically need to implement a bit of this. A robot which grabs memes. I'm reading your idea. It's like basically a more intelligent meme generator. Like I think it'd be interesting to do meme generation when you give a robot like a culture, like you tell it what year it's from, what country it's from, and then it has to generate memes. So this one's physical. So you mean like a literal robot? So that's like, so again, once you're using like hardware, it's a whole different, that's a whole different ballpark. I don't know the Spain one. I definitely know Rickroll and the Flop. Those are classic internet history. How does receive work? So receive's just literally like packets equals read packets. So what do we got? We got to find the next packet. What does that mean? It means we need to find a packet whose sequence bit is equal to the ACK bit, the number of bits we've received. I was thinking one idea I had as a project too. I mean, I did some humanoid robot projects, and dancing. There's like, did you actually know there's a whole competition called robot dancing and robot magic? So there's like research contests where like people try to make dancing robots. It's like, it's pretty fun. It's like a talent show. Let me see. No. So seek. Okay, so when we receive a packet, let me think through this. We receive a packet, when we first send a packet, we're sending SYN, it's 0, 0. And then when they send ACK, it's 0, 1.
So what we're looking for is when sequence
is equal to the number of packets we've received. That's the next one. So if it's 0, we're waiting for SYN. When we receive the ACK packet, it's going to be 1 because we've already received 1. So the criteria is we're looking for the next packet where the sequence number is equal to the number of bits we received, which Copilot is right here. I mean, you definitely could do robotics. You should. I mean, robotics are like fun because they're hard projects, but it's amazing what you can do with it. These carrots are great. I think we're close to leaving the weeds on this. Yeah, we're gonna log this packet. Nice. Unreachable code. Wah, wah, wah. Received packet. Damn, we're at 6 hours. I didn't even realize. Time flew. Time flew by. Oh Lord, we're flying. Cool, let's try this again. Okay, we handshaked. Got a packet. Oh, we received a packet, but we're not sending anymore. I guess the server doesn't send anything else. It just kind of says, cool, here you go, and then it's just like over, because we do this one send command. Let's try sending a few packets. Hey, oh, hey, oh. We're doing like the thing they do in, I don't know what it's called, the hey oh thing, that's what we're doing right now. Let's move the packets. Let's run it. How about receive? How does this work? We need to sleep. I think we're definitely in a good position here. So we've got little things like if we try to scale up the library that's mocked, there's like little things that are hiccupy. I think it just has to do with tracking bits received. So watch, we can actually just debug this and check it out. Cool. Listening. Cool. So we're waiting for bits received 0, right? That doesn't make sense. That's impossible because we've already received the ACK bit. So that just makes no sense. So where are these check for synac? Yeah, basically here, bits received. Yeah, we gotta increment this stuff. And then the ACK packet and the syn packet. Because when we're doing send synac, we've incremented the ACK, indicating that we've received more bits. So that's what's happening here. I wonder if we could just make this logic cleaner by forcing this to be like self dot bits sent, and then this is self dot bits. I thought separating it would have been more explicit, but it's actually turning out to be more of a headache because you could print them in one place and then have them set in another, so the states split. Now it can't be confused because we explicitly say bit sent is 0 at the beginning, and then we increment it after this function is called, nowhere else. And if it isn't set properly, it should be frozen there. Okay, so sequence is 0, ACK is 0. Yeah. Let's go through each of these functions quick then. So that's one. Check for ACK packet. Yeah, we increment here. Send ACK, increase. Send ACK. So in here it should just be again, it's like there. So like these should always be right, essentially. If the state machine is working correctly. So now we can do this again. We gotta clean the packets though, because we got a bunch. Cool. Cool. We can turn off these tests. Yep. Now it should be listening at bits received 2. Yep. And now we're going to go through all our packets. We're going to look at each packet we've received and be like, yo, does this have, is this set properly? It's like, nope, not this one. How about this one? Nope. But up here, we got to do in the send now. We split it. Try this. Well, this would explain why nothing's being sent, because the send function is never being called. Is it because we're bailing here? We never return true. So it never says it was opened, and so it never sends anything. That is not very surprising. Let's try it again. There it is. So now we're looking at each of these packets. There's 3. Sequence. Not this one. Bits received, 2. So I need to see the first time this is called. It should equal 2. Welcome, Danny. Yeah, you're right. We'll build Twitch on Twitch. All right, so we got bits sent here. Is 2. Yeah, that's right. That's exactly what we want. Yeah, so this is dope. We create a packet. Now we've got TCP. Okay, let me see here. So yeah, that's what we wanted. And self, and then what do we got? TCP self.bit send. So we should be able to open this up. We should see sequence is equal to 2. Perfect. We're gonna append the packet, return the packets, and then for each packet, we're gonna save it on the file system. And then at the same time, the client here is now waiting for this. So it's listening, and there, received packet. Boom, it got it. So we have a received packet over file sockets. Now it's listening and listening and listening and listening for more. So technically here, we should be saying we received, bits received, we received half a kilobyte. Oh, so for context, Danny, give you a bit of context. Yeah, I mean, if you're jumping in now, we're, how many hours in? 14 hours in. So over 3 weeks. And basically, yeah, if you code, this is the part that matters. We got some sick code up here where we have a server and it's calling listen and receive. So we just basically give an address and a port, and then we got a client, which is opening a connection, and then we want to send data to the server. And what we're trying to implement right now is like the high level, like we're building all these libraries from scratch. So if you open up listen, we're writing all the code in here to implement the TCP IP protocol, which is like the rules of the internet that the DARPA, like the military, designed back in 1980. So we've got like basically all that defined somewhere here. Yeah, we're following this huge instruction manual, basically implementing all the rules that govern the internet. Um, and then basically we're gonna build the hardware to uh, oh, got it. Well, yeah, basically the goal is the end goal of this project is we want to build a hardware device like a Raspberry Pi, and then send data from one computer to another computer, and then like have the devices find each other, and then send data to each other, all from scratch. Like from scratch, I mean like we're using Python, right? So we're not implementing Python from scratch. We're using certain abstractions, but like we're implementing the core primitives of the internet from scratch, and then also building the hardware to just to say that we've done it. Because I think if you don't build the hardware and actually send data using like Morse code or like light signals, then you can't really say you've built the internet. Like, then you've just built file sockets. Like everything we're doing right now is on the computer. So for context, if you sub, which thank you, I see you did, you can tune in every Sunday, and we will. I think the goal is next Sunday we're going to be doing uh, the hardware part. I have no clue what that looks like yet because I also am not familiar with 90% of what I'm doing right now. But the whole fun part is just learning it. Like that's the premise is uh, doing something that we don't know how to do instead of just like tutorials and stuff that we have done before. Um, and we're seeing how it goes and how long it takes. But so far, it seems like it's about a 20-hour project to get bare minimum MVP. Um, but this is cool. We've got a payload. We're listening. We've got data sent. Data is received. Listening, listening, listening. Um, so we received a couple packets from the server on this machine, and it's aware of them. Um, I think now it's listening for more, as it should. So it received this packet and never received another one. Good question. I think right now I start streaming Sunday morning, so like and I'm in Pacific time, but I'm going back to Mexico and then I'm going to Canada, so it'll be Mexico or Central Canada time, which is like right now it's 3 p.m. Let me do a couple time zone changes. So it's 2 hours later in where I'll be normally streaming, so 5 p.m. Um, yeah, how many hours ago did I begin? I began 6.5 hours ago, and typically I'll begin 2 hours later than that. So, um, yeah, let me. I'll be beginning 4 a.m. PST, so around 6 or 7 a.m. Central Time, to be clear. Um, and this will all be posted on YouTube afterwards. So if you don't get to be in the stream while it's happening, the stream is just a lot of me hitting my head in silence, or well, not in silence, but um, just kind of suffering through debugging things. But that's the fun. It's like my goal with this stream is to just make it as real as possible. So there's no like, it's not marketing. There's no like, I don't know. It's not like a big tutorial. It's not productionized. It's just like literally, we don't know how to do this. How do we start building it together? And then just learn and like, when others join, just like see what's possible. And as I figure out more projects, I want to go through a list of all the things that I haven't built that I've been wanting to, but I've been procrastinating, and then just do it. So, um, yeah. I mean, for context, this stream's coming to an end pretty soon because I just have to go find somewhere to sleep tonight. But I'm just mainly cleaning up a few things so we're ready for hardware on the next time. But thanks for swinging by. Um, yeah, that's exactly why I did it too. Is like I found it really cool to watch other people do streams. So it's inspiring too because you get to see how people do stuff. Um, so I'm very new to it though. I'm just kind of learning as I go. Um, let me see here. What is DNing? I'm not sure. Did I use that term? Uh, let me see. Oh, yeah. Yeah, I am a digital nomad. Yeah. I've been living, well, I'm in San Francisco right now, but I've been living in Mexico for over a year. And I run a company out of San Francisco, but I'm Canadian. So, yeah, I would say I basically haven't had a stable living place in years now, but that's just kind of how I like it. I'm heading to Canada this summer to catch up with family since it's been quite a while. Oh, interesting. This worked. Sending payload. So let's see how the send. Bits sent 101. $150. So bits are being measured again. We're doing a weird ass counting thing. Where bits sent need to be times 8 to capture the size of the payload correctly. Let's try this. Also, I gotta delete packets from last time. I should probably add some garbage collection. That's a good question. Like for how I got into it. I used to do, so when I was an undergrad, I was in Canada. And I did a lot of those like research internships. Uh, that was my exposure. And then I realized I just liked that way more than being in the middle of Canada. Um, and it's kind of weird. Like now I've just been doing it. Like I don't even think about it. I was working in San Francisco back in 2019. And then I left my job, been doing startups, just kind of doing my own thing for the last few years, or I guess a couple years now. And I think when it depends on I think it depends on your work and your school and your life, right? Like if you like traveling and you don't have a job and you don't have like a family or anything or like any reason to be in one place, it's very natural to just travel because you're like you want to go places. So I think that's the situation I'm in right now. Um, yeah, and it's really fun. I haven't been to I visited Australia, but I haven't lived there. Spain and New Zealand are both definitely on my list, and I'd consider my home like Mexico now, and then like my work home San Francisco, and then my family home Canada now. So just based on like where people are, but Mexico City I'd highly recommend if you haven't done the trip. It's amazing. Okay, let's get this committed. Git commit. We got this on Git too, so let me see where it is. I should be able to share it now. And I think here I should probably wrap up this stream soon because now we're getting close to 7 hours. And figure out. Also, Danny, or whatever your handle goes by, hit me up on LinkedIn or anywhere if you want to connect. Happy to chat more about digital nomading. If I can help give any context on like how to get into that more, but I don't. I guess I can put my name. I'm still very new to this Twitch thing, so yeah. If you want to connect on LinkedIn, there's my name. All right. So how are we gonna prep this for the next stream? Yeah, if you're without degree, I think I'd be like, degree definitely helped me a lot because of visas. That's the main reason. Like, it was hard to get into the US without a visa. But then I did internships at like Carnegie Mellon and like US schools. And then, yeah, I got a degree. So that definitely helped. But you can certainly do it without. I just wouldn't be I wouldn't be the most informed person on how to do it without a degree because I definitely used a degree for all my travel. So, but what I do know is there are people who do it without a degree. So, they're just clever. Like, I think a good path is like, yeah, boot camps, get early access into like a startup or like an internship, get a visa through work. Or if you're just doing your own thing, like doing a startup, you can just travel anywhere at any time. So, well, anywhere as in places where you can get a visa. If you're from UK, then you should be able to travel most spots. The US is particularly hard without a work visa, but yeah, it's worthwhile. It all just depends on what you value more, like understanding like what it is you want. But yeah, I'm happy to chat more about it. Cool. So let me see here. I think we're pretty much ready to move to hardware here. Let me run through this once more. We got a couple hiccups on like the sending big payloads, but like we're able to do a full handshake. We're able to send data. Yeah. And we're able to listen for it, print it out. I would say functionally we've done we've implemented file sockets. We can see on our file system where they all are. Here's all the packets. They've been written out. And so now the next step is we got to send these packets over. We got to somehow build Wi-Fi. So like, if I go look here at what that means, we go down here on the networking layer, the OSI model, down to hardware, and we talked about this a couple streams ago, where basically we can do Ethernet, which is wires. We can do Bluetooth. We can do USB. We could send internet using light. We could use pretty much any medium. But we're gonna use Wi-Fi, which I think it's this one, wired Ethernet. No, not Ethernet. It's this one. It's the blue box that we were looking at. 802.11. And there's a bunch of frequency rules, and like my gut is to do Morse code because I think it's funny. But there might be a better way to do this to be faster. We got our specs here. So if you look at a typical Wi-Fi, a wireless driver, it's like at least several meters, versus Morse code is like basically incapable. Like it's like a meter because it's sound. What kind of, and Danny, what kind of work are you interested in particular? I think you mentioned you're doing some like, what was it? I'm just reading the chat. Um, like I saw familiar with Java, JavaScript. Yeah. Um, yeah, I think it, like boot camp, internships. Yeah, the best way for those is definitely just have projects. Like university is good legally. Like a degree is super valuable for legal clearance, but the best career growth that I've experienced so far is just from like actively building. Um, but I'm definitely not somebody who would like shoot down a degree or having like certification because it's such a quick way that people vet you, that it can help. Like it's certainly not useless. Let me see here. Nice. Software is a good one if you want flexibility, that's for sure. Yeah, and to be clear, I'm also early. I don't know, I don't quite know what my career is right now. I'm kind of just like, uh, I want to build really epic stuff and make the world amazing and like do cool things. That's kind of my career. Um, I want to do stuff that is really exciting and makes people happy. And I think engineering is a great way to do that because engineering is kind of like just taking things that people don't think are possible and making them possible, which is the essence of evolution as a society, in my opinion. And I think software is like a huge way to do that because everything's software. Yeah, true. Bootcamp has, uh, there's definitely people who will like shame it, but I think most people just look at like learning rate. Like if you're going through a program and you're learning stuff and you're coming out, you've shipped cool things. I think that matters a lot. Um, okay, so we've broken this down. I think what's left here is I need to be like Wi-Fi driver. Oh yeah, sorry. Let me drop you my LinkedIn quick. How do I do this without blasting my whole Twitch stream with my LinkedIn? One sec. I'll drop URL. There, let me know if that works. It's a funny. Just to clarify my understanding of what a driver is, I'm pretty sure it's the thing that interfaces with the hardware. But I don't want to overload the term. Let me open up my internet again. Because I keep using this term, and it's like, what is a software driver? Yeah, it's software that controls hardware. Okay, that I'm pretty sure I knew that, but it was like, it's one of those things where it's like you don't want to be just completely wrong about it. Um, uh, so, well, we're gonna initialize it. what do we actually need to do with this? This is going to be controlling a Raspberry Pi or an Arduino or something. This is pretty low level. Yeah. Well, I need to think of like it's going to broadcast. It's going to listen. So it's going to be a listen command. This is going to be super weird to implement. I'm just trying to think of what it even... Because now we're leaving software world and we're going down to hardware world. Broadcast is an easier one. A packet. Broadcast a packet to the world. So this is going to be like Morse code or something. And we're going to take in a packet. Well, I guess broadcast is going to, yeah, so we've got a few ways to think about design here. But basically, we're going to scan packets. So now we're leaving the software world. We've stored all these weird binary files on our file system, and we're going to scan. And whenever we see one, I guess we need to use the TCP layer. We can't just like, we can't just like willy-nilly read them out and broadcast them. But I guess we also can, because like there's no reason we can't do that. We've already got the handshake working because we look for files with the proper ACK and SYN flags. So this is kind of fun because like mentally we have to really get out of the thought that we're doing software now, because we're actually not. We're like at this, drivers are a weird thing to program because they're the closest thing to hardware without being hardware, really. Like you're basically writing software, but you're thinking about hardware, and it just trips out your brain if you've been writing software for a long time. So we're gonna hand this something like a Raspberry Pi. And yeah, that's right, Danny, you found me. It's banana. We're gonna have this Raspberry Pi basically listening for a payload, and then we're gonna store those payloads as packets, which is super weird. Like I might have to go read more about like how is a Wi-Fi driver built, because it's like there's so many weird hardware nuances here. But I think the interface we care about is this driver is going to listen for packet data, like in real life, like literally over radio, and save packets on file system. And then the main stuff here is going to read the files and then do all the handshake, the TCP stuff. But basically, this thing needs to actually work with the hardware, listen for radio waves, and then store those on a file system. I have no clue how that's going to look at the moment. It's just kind of like that's what I'm thinking needs to happen to make it work. Oh yeah, good question, Danny, about banana. Yeah, so the problem we're trying to solve with banana is that GPUs are super expensive for like machine learning, and right now, since GPUs are slow to turn on, companies have to like pay to keep them always running. And so we want to make it so you only pay for usage, because you'll save a lot of money. Like imagine you have you're trying to build TikTok and you got to use machine learning and you have like 10 GPUs running. That's going to cost you thousands of dollars a month. versus you might only have a few customers a day early on trying to use it, and you have like spikes. And if you could turn the GPUs on only when you need it, then you're paying um, like per second. So uh, it's like renting a movie versus having to own all the infrastructure you want, or like it's like using Uber instead of buying a car. Um, so in certain traffic patterns, you can save a lot of money by not having to own the hardware, um, or have it always provisioned. So TLDR, uh, we want to make it cheaper to do hosting of machine learning. So then more people do machine learning, and we build more cool stuff. So broadcast a packet. This is going to, well, this is going to do a few things. Scan file system for packets. Broadcast packet to the world over radio. Delete packet from file system. So once it's sent, so this is just going to be like a for loop. And it's just going to scan packets, send them to the hardware, but make sure the hardware is dealing with one at a time. And then it's also going to listen for packets and then save them on the computer. That's basically it. That's what this driver is doing. It's really simple. And then I need to look at like, I guess I gotta put some to-dos, like we gotta buy Raz. Oh yeah, so right now, regarding Banana for GPUs, we use cloud, but we found out how to make it a lot cheaper because we turn computers on really fast. So like, we can load models faster, so you can scale up and down quickly. We've also done a lot of software work, so we can do cool stuff like put multiple models on the same GPU. So like, it's really hard to do that typically because GPU memory isn't as easy to use as CPU memory. Like it breaks. It's just like nobody's written nice libraries to work with it. So what we're trying to do is like put 5 models on the same GPU, so then it costs 5 times less per customer. So we're doing stuff like that. We're not at the scale yet where we own our own GPUs, but that would be a cool path to take. I rather partner with people that own the GPUs right now, but like, yeah, at a certain level, we'll definitely get there if we keep growing which right now we're still growing every week, which is a good sign. It means we're doing something right. Computers. I think Raspberry Pi is the way to go. $15 computer. Darn cool. I just need something that can listen for beeps. Or maybe we could use radio receivers. Like, I don't know, like radio receiver Raspberry Pi. Come on, is that a thing? I don't even know what I'm doing right now. I'm just like, I know that Wi-Fi is implemented using radio waves. So basically, we need, like, if Raspberry Pis can listen for radio, then there'd be a cool path of like, let's just listen for radio waves like this. I kind of have to just riff on this a little before I buy hardware. And then Morse code, that's easy. We can use a piezo. I think there's a hardware thingy. Piezo buzzer, I think they're called. Yeah, piezo alarm buzzer. And these can be, you can hook these up to a Raspberry Pi. You can make beeping sounds, and then you can use that to send Basically, yeah. So sending Wi-Fi is sound waves, then listening for it, versus like doing a broadcast over radio. But radio would be faster, probably, or maybe not. It's a frequency thing. So like we could write an adapter to listen to radio and be pretty dope. I already know what Morse code can be done. So maybe we could research like. Oh yeah, all good, Danny. Regarding questions, it's totally cool. Let me just mentally note take this thing quick. Okay, so like basically audio waves versus radio waves. I think those are different. I'm pretty sure. If they're not, well, that's fine. Oh yeah, and a cool later project I had is launching a CubeSat. Anyway, yeah, regarding living, I get paid by Banana, so I'm an employee of the company. We make money, and we're VC backed, so we're a seed stage company, which means we raised some venture capital funds from a bunch of rich people that believe in us, and we have to make the now we got to make the company grow, which is the next part. Once you have money, so in short, also, I'm an early Bitcoin adopter, so I had a bunch of money from Bitcoin. Not like a bunch, but like enough that I can live a couple of years off Bitcoin. And I had income from a previous job. I was working at Cruise, so I programmed like cars, and it was in California. You make pretty good money doing that, so I've been living cheap off that. But I'm by no means rich. So, so in short, I get paid, but it's enough to get by. And I have savings, but not like a crazy amount by any means. And I won't have money in like less than a year unless we make a company work. So my plan is to just make that work. But on Sundays, I like hacking. So this is kind of my side thing, like building and doing Twitch streams. It's doing fun. And I like doing companies for fun. It's all just for fun, basically. But some things are fun and make money, and some things are fun and don't make money. That's the difference. So let's see here. What even is this? SI4X6, so that's a controller. Raspberry Pi. Okay, so like what is this? What is the output of a radio? Like what does it even tell you? Pins to settle. Cool. FM. Oh, so this is we're getting into signal theory now. So FM versus AM. Damn, first audio transmission was in. Oh wait, so this is audio. Oh wait, what is AM? Amplitude modulation. So if they go farther, they're slower. Nice, this is a good comparison. In the 30s, so these are sound waves. So like technically Morse code is a valid approach. Have a good night, man. Thanks for swinging by. And yeah, hope to see you around the stream again soon. By soon, I mean like whenever I do it. So, and you caught it a good time because I'm just heading off too soon. Detector and a demodulator. What are the advantages of using RF?
more susceptible to noise. How does radio go so far? Like, how's that even possible? Like, why is it if I yell, you can't hear me, but then radio waves can like hit the atmosphere and shit? Radio waves have the longest wavelength in the electromagnetic spectrum. So they can go from millimeter to more than 62 miles. Radio waves are light. Whoa, wait, so they're light or are they not light? Or are they audio?
Using electromagnetic waves, radio waves by Kate.com. Radio waves are used to transfer information over very long distances. The ionosphere is a layer of the Earth's atmosphere which contains a high concentration of ions and free electrons. So the ionosphere is a charged part of the Earth's atmosphere. Let's now compare long and short wave
what the fuck?
and free electrons. So the ionosphere is a charged part of the Earth's atmosphere. Earth's atmosphere which contains a high concentration of ions and free electrons. So the ionosphere is a charged part of the Earth's atmosphere.
Why? Is an ionized part? Wow. What does ionized mean? This is where it's going to be fun because I'll reveal how little I know about chemistry and physics. Requires a negative or positive charge. Negative or positive? Which one is it? Oh, I remember this from high school and I didn't listen. Negative or positive charge. Yeah, so they lose electrons. The resulting electrically charged atom or molecule is called an ion. A net electrical. Oh, so it doesn't mean positive or negative. So an ion is just like a thing with a charge. Protons are positive. Okay, cool. So it's just saying that like the ionosphere is this place that has a bunch of ions, which are protons and electrons. And they're all just chilling here for some reason. Why does it exist? The ionosphere. It sounds like a gent band. Magnetosphere. The magnetosphere. Dynamo. Damn, we're getting into like funky names. It's kind of cool because it's like fiction, but it's not fiction. It's literally not fiction, but it sounds like fiction. Like, isn't that cool? You're like, yo, this sounds like some Marvel shit. And then you're like, nah, this is just the Earth, man. The Earth's cool. Planets are dope. Like, I don't know. That's pretty cool to me. And people are like, oh, I'm sad wizards don't exist. And I'm like, bro, we have the ionosphere. And we have the magnetosphere. We have particles and shit. It's pretty cool. Like, I don't need magic. I got physics, dude.
So I don't know why these exist, but this sounds like this is a thing. It influences radio propagation to distant places on Earth. Okay, so like that affects radio waves. Cool. What was I even looking at? Oh yeah, sorry.
Let's now compare long and shortwave radio waves. This here is a transmitter of long-wave radio waves. These radio waves at long wave are able to diffract around the Earth's curvature. So they can diffract around the Earth's curvature. So they can travel a long way. This is because the long-wave radio waves are able to diffract around the Earth's curvature. Diffract around the Earth's curvature. And they can diffract around mountains and around buildings and around hills.
Did he just say that like 5 times?
So they can travel a long way. This is because the long-wave radio waves are able to diffract around the Earth's curvature. Diffract around the Earth's curvature.
Well, I hear him saying the same thing like 5 times. It's confusing as shit.
Mountains and around buildings and around hills. And they can diffract around mountains and around buildings and around hills. So this here is a shortwave radio wave transmitter. The way that shortwave radio waves are transmitted is via reflecting off the ionosphere and then off the Earth's surface, and that is how they are transmitted around the Earth. So remember, shortwave radio waves are reflected between the Earth and the ionosphere. That is how it is transmitted around the world. So remember, shortwave radio waves are reflected between the Earth and the ionosphere.
Yo, is this guy repeating himself? I'm so confused. Am I just like brain dead right now?
The ionosphere. That is how it is transmitted.
Ha, he does repeat himself. Dude, I thought I was having a freaking aneurysm, bro.
Radio waves are transmitted is via reflecting off the ionosphere and then off the Earth's surface, and that is how they are transmitted around the Earth.
Okay, so these ones go around, these ones go bum 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 bum.
So remember, shortwave radio waves are reflected between the Earth and the ionosphere. That is how it is transmitted around the world. So remember, shortwave radio waves are reflected between the Earth and the ionosphere. That is how it is transmitted around the Earth. But remember, shortwave radio waves cannot diffract around tall buildings, hills, and mountains, so their range is lower than long-wave radio waves. But remember, shortwave radio waves cannot diffract around tall buildings, hills, and mountains, so their range is lower than long-wave radio waves. It's question time. Tell me these questions to check your understanding.
2. 1. Fuck.
So FM
Shit.
television radio waves must be in
See,
line
man,
of
this
sight
is why I sucked in school. It's because
of the transmitter. They must be in line of sight of the transmitter. So
okay, so small radio waves are good for us. That's what we need. The big ones are doing other stuff. They just they curve around. The small ones seem like they get the job done. They're short distance. It's a lot of wave questions. A lot of stuff I do not need to know right now. But what I do need to know is how to set up a Raspberry Pi to use waves like this to do these things. Let's look at their project. So like part of me is thinking doing radio is the way to go here. I just think I don't know enough about how to do radio. So I might need to spend some time actually exploring this a little bit more. So like Morse code, easy. I got that. But I'm really trying to think like, okay, packet size is like what's the range of audible? $200 to $8,000 is human speech. Oh, I gotta learn. I gotta like review hertz. Hertz. One cycle per second. Whoa. Oh, so there's. Damn. So a gigahertz is like a million hertz? Holy shit. 100,000, million, 10 million, 100 million, billion. Gigahertz is a billion hertz. Wait, so you're saying human speech is like 100 hertz? Alright, so radio waves are way higher frequency than audio waves. That's cool. So a hertz is a cycle a second. So radio waves are like a billion a second, which means you can send way more information, I imagine, through a radio wave than you can through audio. I think I'm gonna have to spend some time grokking this a little more. Just like I could do it off stream, but the whole point of the stream is like, well, there's gonna be streams where it's like I do software, like I just don't know. I don't know what the things mean. So kind of like at the first stream where it was like, what's the internet? We just had to kind of learn what that was for a couple hours. Like, I think I have so many questions about how radio works and like what it means to scan radio waves. Like there's just so many unknowns that it's like I might have to spend just like a stream just trying to understand that and then buy hardware. Like once I actually understand. So okay, basically let's scope this out. We're hitting territory where it's just like, yo, I don't know shit. Next time on live stream. What are waves and radio waves and sound waves? How is data sent through radio waves for Wi-Fi? Raspberry Pi support for radio wave receivers. Broadcaster. Physics of waves. That'd probably be good to know. Need to understand some physics. I don't know. I have so many questions. Like, I basically need to have a mental model of like signal theory a little bit more. It can't just be this like completely unknown thing. What else do I need? Like for bare minimum to build a
Wi-Fi driver adapter.
Well, I'm gonna need so I need to refresh on programming Raspberry Pis, like hardware, and I need to refresh on like the different hardware tools needed. And I think this is good. And I'll probably go like down like 50 rabbit holes like I do. So I think we need a stream for like following curiosity, figuring out like exactly what needs to be built. So the output of the stream is what parts to order, spec. Yeah, I need to know like what for TCP packets. Reliability. Yeah, so I need to have basically a sketch out of like what a adapter is going to look like. If I was a hardware person, I could probably just like start building, but I am not, and so I must learn things to begin doing more stuff. Anyway, this has been a fun stream. It's crazy that it's more than 7 hours. Like I didn't even realize that so much time passed. It's kind of insane, honestly. Gonna post videos on YouTube because Twitch deletes my videos, and I'm excited for next time. And I'm happy that so many cool people showed up during the stream. So that is all for tonight. We're gonna end at 7:11. So take care, everyone.